Good morning, everyone, and thank you for joining us today. I'd like to welcome you to the fifth Innovation in Atmospheric Measurements Techniques virtual workshop, partnered with EU Green Week. The workshop is organized by the Climate and Atmosphere Research Center of the Cyprus Institute in collaboration with Actris, IAGOS, and IGOS, and supported by the EMICARE, Edu4Climate, and ENVINOV projects. My name is Eleni Zinanos, Project Officer for Communications and Dissemination here at the KRC, and I will be guiding you through this workshop. I would also like to introduce you to my colleague Urania Marcu, who will be helping us during the workshop. We have an exciting program with about 35 talks reporting on the latest innovation in the field of atmospheric sciences, and it's great to have so many of you already here with us. Many thanks to all of the presenters and chairs for making this possible. Feel free to share about the workshop on social media using the hashtag Innovatmo25 and EU Green Week, which we will share with you in the chat. In terms of the structure for today, we will start with the opening session, followed by 26 oral presentations and closing with 11 VPCO presentations. Throughout the workshop, you'll be able to submit your questions for the oral presentations in the chat. Your questions will be reviewed and passed on to the presenter by the chair. And due to time limitations, we might not have time for all of your questions, in which case we might be able to pass on your question to the presenter and they can get back to you directly afterwards. We should also remind you that this workshop is being recorded for monitoring and reporting purposes and for the promotion of future events. As a reminder, each presenter will have 7 minutes for their oral presentation, followed by 3 minutes for questions. For the VPCOs, each presenter has 2 minutes and there won't be any questions afterwards. We do have a full program today, so a kind reminder to stick to timings. I will be keeping time, giving presenters a reminder when time is up or if they're running late, to ensure we keep the flow of the program. Again, please remember to submit your questions for the oral presentations in the chat. And without further ado, I will pass the floor to Professor Jean Xia, the Director of the Climate and Atmosphere Research Center here at the Cyprus Institute and Coordinator of EMICARE, for an introduction to today's workshop. Professor Xia, the floor is yours.
So, welcome again, everybody. And I wanted to give you a short, brief introduction before we start all the presentations. I wanted to give you a piece of memory of when we started this workshop was 5 years ago, a few months after the COVID. And we have established this workshop for keeping in touch, all of us, on the latest innovation developments in atmospheric sciences. And it has proved to be very successful over the years. So that's why we have kept this format of online meetings, where we have a lot of presentations from different categories of presenters, from universities, research institute, and also from companies presenting their latest developments. As mentioned by Eleni, this is organized by the Cyprus Institute, but we are supported with the 3 European research infrastructure in atmospheric sciences, which are Actris, IAGOS, and ICOS. And the scientific committee is reflected here by colleagues from these different research infrastructure. I will not name all of them, but I would like to thank each for their contribution in the review of all the abstracts, in the drafting of the program, and also some of them will share the sessions of today. As mentioned by Eleni again, this has been organized by the Institute here in Cyprus and supported by several European projects, EMICARE, Edu4Climate, and ENVINOV. This 5th online scientific workshop has registered so far more than 270 participants. It's almost a record, and from 52 countries, and this is the map of the number of participants. So we have a lot of participants from Europe, of course, but also a growing number from America, from India, China, etc. So it brings more attention, not only in Europe, but also in other parts of the world, and which is a nice key performance indicator for this workshop. A lot of research organization participants, university, research institute, a little bit of public and private. Today we have 37 presentations from 21 different countries, and they are listed all here. So, and with most of the presentation from university and research institute, but also a good amount from the private sector you will see later on. This is some links you can use for the previous workshops because all these workshops are recorded. So if you would like to attend specific talks or you can find the program of the previous years, just go there on this link and you will find the record of the workshop and find the presentation you are looking for. I realized that after these 3 years, I'm still wearing the same T-shirt and then I have still the same background from 23, 24, and 25. So I guess next year I will have to keep the same thing. Right, so I don't want to take too much of your time. I would like to thank for your participation. I would like to wish you a very nice and interesting innovation workshops. I give you here the floor, Eleni, for the next part of the program. Thank you.
Thank you, Jean. Thank you for your introduction. And now we'll introduce our first chair, Professor Stéphane Sauvage, who will chair the session on VOCs. Stéphane, are you with us? Stéphane, can you hear us?
I'm happy to play the joker, Eleni, of Stéphane.
Okay, Jean, if you would like to, maybe begin and then hopefully maybe he
you are here.
Excuse me.
There he is.
I'm sorry, I have an issue with to find the button for my camera, and so I can start without my camera. So sorry for that. So thanks a lot, John and organizer, for letting me sharing this session. Session on VOC. You know that VOCs, volatile organic compounds, are more and more of interest, and it is quite challenging, especially to put in place some monitoring measurement sites. So we have a session with several new developments for VOC monitoring. So I will give directly the floor. So we have 7 talks this morning for these VOC sessions. So we will start immediately with Veronika Poposilova, sorry for the pronunciation, from Top Work in Switzerland. So the floor, Veronika, is yours. Please keep the time. You have 7 minutes for your talk. Thanks a lot.
Hi, everyone. Can you hear me?
Yes.
Yes, perfect. I think I need to have the rights to share my slides, to share my screen.
If you tried sharing, we should get a request and we should be able to let you share your screen, I think.
I do not even have the option actually. To share. Yeah, I don't have the option to share my screen.
Based on the setting, you should be able to. Would you like to just quickly forward this to us and maybe we can share it on your behalf? Or
okay, now I see it. Wait.
Can you see it?
Okay. Yeah, it just popped up. Okay,
great.
So you should see my screen now.
Perfect. Yes, we can see it.
Okay, and there should be nothing side mounting. I'm gonna go to presenter mode. See? Okay, does this work?
Yes.
Okay, perfect. So sorry for this small delay. Yes, so hello everybody. My name is Veronika and I'm leading the air quality market at TOFWERK. And today I would like to talk about the instrument that we are releasing literally this week, which is called AirTox Monitor. And it's targeting simplified VOC monitoring with our next generation PTR reactor. And before I jump into the technology, I would like to quickly just run through why VOC monitoring matters. So there are numerous reasons why people are interested into monitoring of VOCs. The VOC play a key role in understanding the atmospheric chemistry. They contribute to ozone formation and also secondary organic aerosol production. But VOC monitoring, we should not forget, is also essential for protecting public health and ensuring regulatory compliance, or it can be useful for enabling fast emergency response, for example, during some industrial chemical accidents. So about the technique, so I work for TOFWERK. We are making time-of-flight mass spectrometers, and I try to guide you a little bit through how the technology works. So we need reagent ions to ionize our sample, and these reagent ions are produced in ion source. In the AirTox monitor, we are using H3O plus and O2 plus as reagent ions. And we track our sample into the ion molecule reaction chamber, and here the VOC react with the reagent ions, and they are ionized. So we need to ionize them in order to be able to measure them with the time-of-flight mass spectrometry. Then the created ion beam is focused, the air is removed, and the ions are extracted orthogonally into our time-of-flight chamber, where the ions are separated based on their mass-to-charge ratio. So it's very simple in a principle, but this tool basically gives us really big advantages in comparison to other traditional techniques, for example, offline methods. And this is the real-time measurement. So we have very high time and spatial resolution. Also, if we move the instrument, we have very low detection limits to sub-PPT levels. The ionization is soft, so we are most of the time conserving the molecular formula. And we have broad chemical coverage, as you can see on the bottom. This is basically the spectrum that we get every second, while one of these peaks represents one or more molecules. But when we are talking about simple VOC monitoring, there are still some limitations because the instruments we are talking about are still mass spectrometers. They are fairly complex instruments. They often require a highly trained operator. They involved extensive training, time-consuming post-processing, and unfortunately still lack the robustness for unintended 24/7 field deployment throughout the year. So our goal was to simplify the VOC monitoring without actually sacrificing the data quality. So we want to go from this to basically obtain reliable VOC concentrations for the operator immediately, while maximizing the analytical accuracy that we can achieve these kind of instruments and minimizing the effort for the user. So this was the motivation to introduce AirTox Monitor. So this is our solution for monitoring in industrial and environmental regulatory research for mobile deployments. And the three pillars that we focused on was the robustness, usability, and high performance. So I cannot talk about, within the 6-7 minutes, I cannot talk about all the improvements we did, but I'm going to focus on a couple. So to improve the robustness, we have replaced our reagent ion source. So we have been using, or we are still using, the plasma source. With the AirTox monitor, we are putting a new VUV source. And we also put as a standard the diffusion source for mass calibration for improved and stable mass accuracy. We have heavily worked on our software, so the AirTox monitor comes with Focus Track, which has plenty of workflows implemented that I'm going to mention a bit later. And altogether, this creates generally lower need for maintenance for the user. But we clearly wanted to keep the high performance of the instruments, so we are using TOF with up to 3,500 mass resolving power. And because we are using the VUV, we also can switch rapidly between PTR and O2+, which expands our real-time compound coverage. So what's new, or why we are using the VUV light? So this source basically has a lamp, so vacuum ultraviolet light source to generate electrons by striking a metal surface. And these electrons are accelerated and they interact with the introduced gas, which is water. And this creates the ions that we want, so H3O plus reagent ions. As you can see in the figure on the right, in the right corner, the VUV source generates high purity reagent ions. So the dominant peaks are most exclusively the primary reagent ions, H3O plus and its water cluster. And this also leads to lower levels of undesired charge transfer signals. So this is an example here for benzene, where we have the charge transfer peak for about 4% of the main peak. So as I said, the main issue why we replaced the plasma source was the stability, especially the long-term stability for extensive usage. So we tested this source for more than 3 weeks now. Now, currently, it's been longer, but I only have data for these 3 weeks. And we have basically set up the measurements in Thun in our office in Switzerland. And the AirTox monitor was configured to automatically switch between PTR and O2+ every 10 seconds. It was continuous. And in the top panel, I am showing basically the sensitivity calibration data for benzene in both of these modes. And we can see that the values remained fairly stable across the entire measurement period. We didn't encounter any issues. And the bottom panel shows the real-world concentration that we measured for selected species, basically measured it either in one of these modes. So the VUV PTR reactor, it brings many improvements. I cannot talk about all of them, but I try to summarize them quickly. So it brings higher stability. The reagent ion purity is better in comparison to our older sources. We have fast switching. Our detection limits are improved because we are avoiding a peak tubing that we had in the past. The maintenance it's improved. We have inserted a pinhole that is basically easily cleaned than the capillary in the past. And we also have a dedicated low pressure port if customer wants to connect this to a GC. And now I would like to talk a little bit about the software. So the PTR, the SIMS technique generally gains more popularity with new users that are not used to SIMS. We also have instruments in industry and regulatory agencies. So there was definitely a growing demand to make the instrument easier to use. And this was really the motivation to develop Track and improve it. And we are still keeping improving it based on feedbacks to provide the intuitive software interface. So to summarize the main features, like this small video. So the Track has fully automated routines. So we have now real-time mass calibration. So you don't need to stop acquisition to mass calibrate your time of flight mass spectrometer. There are automatic sensitivity calibrations. The software basically exports you immediate results, immediate concentration of targeted time series with background subtraction. We have implemented performance checks, so it makes it easy to identify if there is something wrong with the instrument. Clearly, it comes with the compound library of the most wanted air pollutants. And we also have a history of calibration results for quality control of the data towards the past. And I think I'm running out of time. So as a conclusion, so I have talked very quickly about the new AirTox monitor with the new generation PTR reactor and Vocus Track. And as an outlook, we still keep working towards implementing more software features for making the data reporting more reliable and as accurate really as we can with the PTR method. And we appreciate any feedback and suggestions from Track users, so from current Track users that have the latest software version. And we are definitely open for collaboration to deploy the AirTox monitor to the field, to stress test this and get feedback to, further improve it. And for this, I would like to thank you for your attention.
Thanks a lot, Veronica, for this very clear talk. We have one very general question on the chat by Esmuel Yerushalmi about if the Toxi monitor you're presenting support already reduction air and soil pollution in urban area and industrial area. Maybe we can formulate the question. Do you have already such instrument deployed in, I don't know, in a monitoring network, or have you already a plan to implement such instrument in a monitoring network? I don't know, Air Quality Agency, research monitoring network worldwide.
Yes, so we had the model deployed. We had it in now in 3 big mobile vans in the US. So for EPA, so Environmental Protection Agency, we have had it for 1 month at the Ascent station. We are planning to do some measurement at the Actry station, basically comparing with other existing techniques that are at the station. And but sorry, we have not had the instrument yet with the VUV source. This is something really new, and that's why we also want to stress this. But this is basically the plan, and this is also why we want, to collaborate with the community here and be open to ideas, basically, where we can, demonstrate the capabilities and get feedback, basically, from new users.
Okay, thanks. A second question about calibration and blank. What is your advice, and what do you plan to ensure the metrological traceability of your measurement? Is it better to use a calibration unit, for instance, with automatic blank and calibration? What do you plan for that with this TOX monitor?
So we typically rely on calibration cylinder, and that we recommend always to the customer, and we are using it so-called primary standard. So we calibrate in-house to the whole library of the compounds that we provide as default, and clearly in the library there is small molecules that we have in the primary standards, but we are linking the sensitivities basically to chemically similar compounds that are in the cylinder. So when the customer has the instrument on site, he can set up calibration, every day, every week. Really depends. It's automatic, so it's a cycle that he can set up as the community or the customer agrees on. And every time you basically calibrate, the sensitivity factors are adapted based on the calibration. So and this is tracked, so you can basically go to each specific compound and see how the sensitivity evolves within the time. So after 1 month, if you do daily calibration, you have 3 data points, and you can clearly see basically if this deviates, let's say, more than 20%, or if this goes down, you can see that there is something maybe going wrong with the instrument, or it's your inlet is getting clogged, etc. And for the zeros, so this is separate. So we have another cycle for background measurements that are customizable. So you can measure 5-10 minutes background every 2 hours. It depends how much data you actually want to sacrifice. And these backgrounds are basically, interpolated kind of and subtracted basically from the further measurements. So the Excel files that are exported of the concentration of the data are already subtracted for this background.
Okay, thanks a lot, Veronica. So we are, the timing is running. So you have another question on the chat, if you can answer the chat directly. So we will move to the second talk from Marcus Lemminger from Unicon. Marcus, are you online?
Marcus is not here, but
okay.
I'm here. I'm jumping in for Marcus. And
okay, no problem. So you can share your screen. Thanks a lot, Veronica, again for your talk. And okay, we can see your screen.
All right.
In full mode. Yeah. Okay. Perfect. Thanks.
All right. Hi, I'm Tobi Reinecke. I'm jumping in for Marcus today because unfortunately he cannot be here, but I'm very happy to talk about our novel solution for automated real-time monitoring of atmospheric VOC, the so-called VO Sentinel. So let's directly jump in. So the backbone of the instrument is our PTR-TOF 3000, which is a proton transfer reaction mass spectrometry system. And it's comprised of basically 3 parts. On the front, we have our Invion ion source, which very efficiently produces our primary ions. Ionic and neutral interferences are efficiently removed, and that's how we end up with the purity of about 99% of the primary ions. Additionally, this ion source enables very fast switching between the different primary ions. The ion source is followed by a drift tube reactor, and here we ionize our VOC via soft chemical ionization. We control the conditions in the reactor, so we have a very well-defined, predictable ion chemistry. All wetted surfaces are treated with our EVR, extended volatility range technology, and that leads to very fast response times. On the back, we have our time of flight mass spectrometer, where all the ions are separated and detected. Let's take a closer look at the ion source. As I already mentioned, we can cycle very fast through the primary ions. And here's a typical ionization pattern we would use in the VO Sentinel. So we would start with ionization in H3O plus mode and with a high field strength. Then we would reduce the field strength, the voltage to go to a medium field strength, and then we would, in the next step, further reduce the drift voltage to go to a low electric field strength. Then we switch to O2 plus ionization, again at a high field strength, and then followed by NO plus at a low field strength. This complete cycle takes about 1 minute, and then we would repeat this over and over again, like you can see here in this pattern. Even though we constantly cycle through the different ionization modes, instrument stability is not affected at all, as you can see here for this 18 days constant measurements of cycling for, as an example, acetone and benzene. The sensitivities stay within the precision of the instrument. Standard deviations are significantly lower than 10%. Another feature that is implemented in the system is dynamic humidity control. So certain compounds, like this example here, like formaldehyde, show a rather strong dependency on the sample humidity. As you can see here, when we change the humidity in the sample, the sensitivity of formaldehyde is reduced in classic PTRMS. However, with the active humidification of the sample, we can regulate the sample humidity and stabilize the sensitivity of the formaldehyde. So that means by stabilizing the humidity, we have a true humidity-independent detection of VOC, and that in turn stabilizes our ionization patterns for the VOCs. The whole system is operated by our AME software. AME stands for Automatic Measurement and Evaluation Software. The software automatically cycles through the multiple ionization modes. We have real-time data evaluation, fully automated. So there's averaging, background subtraction, peak fitting, and most importantly, pattern matching. So user interaction is absolutely minimized in the system. So just to wrap this up a little bit with what I told you. So the VO Sentinel is basically a combination of our PTR TOF 3000 with humidity control to have a robust matrix combined with quick switching, and everything is fully automated with the AME software. Now I would like to show you a measurement example for isoprene. So there is a recent paper that showed that isoprene measured in urban environments can have significant interferences from the fragmentation of aldehydes. So what we see here in this measurement is that mass 69, which would usually be attributed to isoprene in PTRMS, is not only does not only come from isoprene, but also from fragments of certain aldehydes. That means in this measurements, if we would only use PTRMS without GC separation, the isoprene would be overestimated. But with the VO Sentinel, we do not only have the information of one ion mode, but we have all the informations from cycling through the different ionization modes. And this allows us to train the pattern matching algorithm. And here is a measurement where we tested the pattern matching. So we injected a constant concentration of 9 ppb of isoprene and spiked the known interferences to the isoprene. And as you can see here, with the peak fitting and pattern matching, we can actually separate the isoprene signal from the known interferences, even though the interferences are of significantly higher concentration than the isoprene. And then I would like to show you another example where we measured isoprene in Innsbruck in Austria. So this is an ambient measurement. And again, this is the trace for mass 69 without peak fitting and pattern matching, this would all be attributed to isoprene. But if we now apply this algorithm implemented in the VO-Sentinel, we can actually see that there are numerous contributions from the aldehydes to this signal, and only a small fraction of the MAS69 actually comes from isoprene. And this already brings me to the end of my talk. So the VO-Sentinel is a robust PTRMS analyzer for automated air monitoring, which delivers quality ensured data of a wide range of VOCs from anthropogenic and biogenic sources. And the combined pattern matching and peak fitting at the different ionization nodes significantly reduces potential interferences. And as of yesterday, we started deploying this instrument in the Innsbruck Atmospheric Observatory, which is part of the ACTRIS National Facility. Yeah, and we initially start with about 15 to 20 VOCs for constant monitoring. Yeah, this is the end, and I'm happy to answer any questions you might have.
Thanks a lot, Tobias, for this talk. I cannot see any question on the chat, but I have one question at least.
Sure.
So you mentioned the example of isoprene. So do you have another example already in place, for instance, monoterpenes?
Sorry, for what?
Yes,
Again?
for other, you gave this example
Yeah.
about isoprene and the separation for isoprene, which is nice, really interesting. And do you have other species on which you have already worked to test this process?
Yeah, so in general, we have a list of those 20 VOCs, and we train the algorithm to actually match with the. So we need to train the algorithm with a pattern recognition. So we measure the fragmentation patterns, the ion distribution in the spectrum, basically product ions, and then we can very stably monitor those ions.
And this data process is online, or you have to
No, this is fully automated online. So the user, the user does basically does not have to do anything. So the algorithm, all the cycling, the data evaluation is all fully automated and integrated in the system. So we directly get an answer or the concentration of the VOCs. So this is a monitoring solution and not a scientific device where you have to interpret your data by hand.
Okay. And when you say long-term measurement in Innsbruck, the idea is to leave this instrument for a very long term at this station with this idea to have a labelization of this measurement afterwards.
Exactly. Yeah. So I think it's supposed to be there for about a year.
Okay. Okay. I can see a question on the chat from Liselott Tinel. Is raw data still accessible through, and in case new interferences appear that are not integrated already in the software?
Yes, raw data is collected. Yeah.
Okay. Okay. There is another question, but please could you answer on the chat directly, because we have to move to the following talk. So thanks a lot again, Tobias, for this presentation and for your answer. Thanks.
Thank you.
Thanks. We move now to the third talk from Audrey Grandjean from Chromatotech. Audrey, are you online?
Yes. Do you hear me?
Yes.
Okay.
It's a little bit noisy.
Oh, is it?
No, that's okay. That's okay. I think we can deal with it.
Okay.
Okay, we can see your screen. Yes, perfect. So the floor is yours.
Here. All right. So hello. This is Audrey Grandjean, and I will present you a study on the generation of formaldehyde using a paraformaldehyde.
Audrey, we have some issue with the sound. It's sometimes cut.
I think I don't have any other options.
Okay, try like this. Yes.
Do you hear me better now?
Yes, looks fine. Looks fine.
Try to just like articulate, I guess.
Okay. And a bit louder, please.
Yes.
Okay.
Yeah, I'm still sharing. All right, so okay. So formaldehyde is a pollutant, mostly present indoors, and it is in atmospheric chemistry. And to monitor accurately formaldehyde, we need a reliable calibration method that can also be used as a result validation method. In other words, we need a dynamic generation system. Formaldehyde is industrially produced via catalytic conversion of methanol, and in laboratories we can find commercially available formaldehyde cylinders. A variety of lab-scale systems have been developed involving aqueous formaldehyde evaporation or depolymerization of paraformaldehyde or trioxane. And along with cylinders, about this, paraformaldehyde permeation tube is widely spread. So having recently developed a formaldehyde analyzer, we chose to base our generation system on the use of paraformaldehyde permeation tube. Because unlike formaldehyde cylinders, it offered better flexibility in terms of concentration range and better portability or integration into our type of analyzer. This, as well as lower risks, considering it is not pressurized gas and it is not highly concentrated. So you can see two examples of permeation tubes on the right. This consists of a tube or a vessel filled with paraformaldehyde powder and closed by a membrane that is porous to formaldehyde. When heated, the paraformaldehyde depolymerizes into formaldehyde and then permeates through the membrane that is porous to formaldehyde into a stream of pure gas that we supply. The concentration of formaldehyde depends on the temperature, the gas flow rates, the membrane dimension, and the membrane materials. The target characteristic of our system are for it to be integrable into an analyzer and to generate concentration in the indoor air range of concentration. This is the assist system that consists of a permeation tube placed into a temperature-controlled oven and supplied by a constant flow of nitrogen to generate the formaldehyde mixture. We varied the temperature and the nitrogen flow rates and analyzed the resulting concentration using a continuous monitoring formaldehyde analyzer. And also throughout the year, we did punctual sampling using the standard method involving deep pH sampling and analysis by HPLC UV. So this allowed us to determine the stabilization time, the range of concentration, and the overall stability of the system and the permeation tube. Here you can see the emission rate, so which is the amount of formaldehyde emitted per minute throughout the year at the 4 temperatures tested. The system was used intermittently throughout the year, and 97% of all the values were within plus or minus 10% of the average, demonstrating excellent stability of the emission rates and thus on the concentration we want to generate, regardless of the temperature and for over a rather long time. The second graph here shows the concentration of formaldehyde as function of the reverse flow rate. And the concentration ranged from 33 micrograms per cubic meter at 100 milliliters per minute and 50 degrees to 464 micrograms per cubic millimeter at 65 degrees and 30 milliliters per minute of nitrogen. So the slope of these regressions correspond directly to the emission rate of the tube at a set fixed temperature. So this shows us that the emission rate of the permeation tube is only dependent on the temperature and not on the flow rate. So since the emission rate seems to depend solely on temperature, I use the empirical Antoine equation to express the emission rate as function of the temperature. That's what you have here, emission rate as function of the temperature. And all 68 data points that were measured throughout the year all fit here on these spots and fit the linear regression perfectly. So the same behavior was also observed when using a second custom-made permeation tube that emits at a much higher concentration. And this linear regression is extremely useful because by certifying a tube at two temperatures, we can determine the A' and B constants and use the tube over a whole wide range of temperatures with accurately predicted concentration. And here you can see the concentration generated as function of time after starting to heat the oven at 55 degrees, with each plot corresponding to a different flow rate of nitrogen. And from the exponential growth feed here, I could retrieve the stabilized concentration value for each condition, finding that it took a maximum of about 1 hour for the concentration to stabilize under all conditions. And you all know that fast startup can be an asset for monitoring a campaign where time is often limited. So to conclude, the system design was able to generate formaldehyde concentration within the typical indoor air range. It is compact enough to now be integrated into our formaldehyde analyzer, and you have an example of a standalone calibrator system here. So it can be used as like calibration system and also just result validation continuously, like just a check, a result check. And it has a fast stabilization rate and a good stability over a year of measurement. So additionally, the relationship between the emission rate and temperature can be used to predict the concentration to be generated accurately. And we observed that to determine the emission rate of this tube, the standard method with DMPH and HPLC UV was faster and more reliable than the typical weight method for permeation tube, because unlike the weight method, the standard method does not measure the water that is lost also during the emission. So that is how we certify our tubes now. And I thank you for your attention.
Thanks a lot, Audrey. I do not see any question on the chat. One question, so first of all, it's really interesting to have such a system to generate a reference mixture for formaldehyde. It's really useful. I guess a key point is to have a good zero wear to flush the membrane of the tube. Do you have test something, or what is your recommendation on that?
So I used during the test, I used nitrogen cylinder, and it's it really has traces of so we can so this is like maybe the purest we can get. So even if we have traces of it, we cannot notice it because it's like under 100 ppT levels. So it's really low. And if we want to generate at low concentration, we need like really pure gas. So
meaning that the final mixture is in nitrogen matrix? but not in zero air, or you dilute, maybe I missed something.
Yeah, no, I dilute in nitrogen, not in zero air.
Okay, so
this is something we actually want to test, is like use zero air instead, but we don't know yet if it can impact.
Yes, because yes, certainly the matrix is really an issue with the formaldehyde analyzer if you use only nitrogen, but I guess you are in dry nitrogen, and then
Yes, it is
test with zero air and humidity maybe it could be a challenge, but yes, okay.
Yeah, I also did tests, but for another study with humidity, but I added humidity later, not directly in the oven. So
Okay.
I did some dilution with humid air.
Okay, and last question, is it portable? I mean, could you move this your generator from a seat to another site? Can we go for a transfer standard?
Yes, so it is portable. I mean, we need to supply it with electricity and supply it with a pure gas. But
Yes, meaning that you keep the tube at temperature, at a certain temperature during the transport.
No, just room temperature.
Okay.
And since the startup for the formaldehyde, at least the stabilization is fast. That's why it can be just brought on site and be stabilized on site. So it is fast stabilization.
Okay, thanks a lot, Audrey. So we have to move. So if you have other question for Audrey, please write on the chat. So we go for the next talk. Thanks a lot, Audrey, for your talk and your answers. So the next talk is from Jan Wozniak from Picaro. So Jan, yes, you are connected, so you can share your screen.
Hello, good morning.
Good morning. So that's okay. The floor is yours for 7 minutes.
Hide this. Do you see the screen correctly, or do you see all the windows on top of it?
No, it's correct.
Okay, because I still see some. Need to minimize it. Okay, I think I'm good. Good morning, everyone. I'm Jan Wozniak from Picaro. I'm a senior field application scientist, and I'm here to present some of the work of my colleagues. We are developing a new approach to measurement of VOCs. So let me quickly run through those slides so we keep in time. Wait, okay, this works like this. So the plan is to tell you about a bit about the cavity ring down spectroscopy, although I basically cut it very short, and then tell you a bit more about how we develop our VOC analyzer, and then show some data from real measurements done last autumn in Berkeley. So in our standard instruments, maybe you are measuring formaldehyde with one of our instruments. We have those as well. We measure with a narrow band spectroscopy. So we take a laser light and scan for those small, tiny peaks of the small molecules to catch their absorption profile. The idea is to fit the shape that we see to the measured points and then get the height of that peak, which also allows us to tune very well because we can auto tune depending on the shape and how good it fits. If you take that narrow band line and you show it in a like zoomed out setting in a broader band, you see that there are many more lines available. So we chose this one for methane, but that's not all the story, because now when we can use broadband lasers that can tune in those broad bands, we can start seeing much more. So as you can see a bit below, you see methane and ethylene, which give you those small tiny peaks. But if you look at those bigger molecules like propylene on 1-butane, you see that they absorb in a different shape. So they don't absorb anymore in narrow peaks, but they absorb in broader shapes. So the idea is now that we can measure the broad spectrum is to try to recognize those shapes and try to use them to detect the VOCs that they represent. We are currently working on our spectral library. It's over 600 compounds, and we keep on working. We are not stopping at those 600. So it means that we can recognize any of those recognized 600 compounds by their shape, right? And we can compare them against the other shapes that sometimes they are similar, but they can always have some features that allow us to recognize one from another. Here's a nice example of a few shapes that would otherwise give you problems because of the same mass. But for us, you can see that we can see some differences between them, and using algorithms, we can detect and tell you which are present in your mixture. That's what you will see when you get just the raw data. So you see points. You could ask why there are points, where is it like not a smooth line, but we try to omit those places where those small peaks that we saw before are, and they are always present, like water, methane. So we choose our points carefully, and here's a little literature reference. But I wanted to show here, like, how do you recognize what's underneath? So we employ a hunting algorithm that tries to detect what mixture of gases is inside. So you saw those dots on the previous slide, and here is those same dots, but with the fit result and with the results of all the gases that were detected in the mixture. This is our calibration mixture. So we know what those are, and I can tell you that we detected without any miss all the 13 calibrants that are in that mixture. Let's move to the autumn session. We did this in collaboration with Professor Alan Goldstein Laboratory at UC Berkeley. And from here we have some data. Maybe it's also worth to mention that there was a construction site nearby, so we expected to see some events that will show different than the background. And we also run the PTR MS instrument for comparison. You can see here the long range, like all the detection, those are the like total VOCs, which show just the total area of the VOCs measured. And if we zoom in into that 3rd of October, we can see that we had an interesting spike, an event, and we could detect that it's a third butyl acetate. Here is the fit, so our hunting fit results that show you that the third butyl acetate is a great agreement with the detected VOCs. And here's another interesting one that shows you, for comparison, the PTR technique could have a problem with identifying the third butyl acetate because it would break into another parent ion. So you can see that we have it in gray, that it would, represent something else, and it will be difficult to recognize. And thanks to our technique, we can recognize those VOCs better. And well, we are solving some of the challenges, but we are not, we might not be as sensitive, but there will be advantages and disadvantages of this system. But so far, we are detecting very well all the VOCs that we have in our library with great agreement. And we are expecting to publish soon in AMT with more reveal on what the instrument can do. Currently, this is still work in progress. There is no product that we can sell you, but we are actively looking for cooperation from any interested parties that we can test this together in the future. Thank you so much.
Thanks a lot, Jan, for this presentation and very promising monitoring system. So first question from Liselott Tinel, what is the LOD, the limit of detection you currently obtain for the main compounds?
So as it is, the instrument just measuring from ambient air, we are talking somewhere from single ppbs, depending on the compound. So some compounds, it will be 10 ppb, some compounds will be 1 ppb. If you attach some GC in front or some preconcentrator, you could go into the PPD ranges. But as it is currently like used just online, like a regular Picaro instrument, it gives you those ppb limits of detection.
Yes, and Veronica asked if the humidity is a problem, and if the limit of detection you mentioned are for 1 second of 1 minute of integration.
Those are good questions. We are usually at few seconds data rate, so like 5 seconds, 3 seconds. The humidity is not a deal breaker because we measure the water content as well, right? So we can correct for it.
And a last question, is the ambient air matrix is really an issue if you have an evolution or if you are in different situation, industrial area or urban area or background area, do you have to learn again with the instrument in order to have a good separation of the compounds?
Those are great questions. So basically, we have that hunting algorithm. This is all still work in progress, but it can detect very well all the VOCs. But of course, if you know exactly what's in the air, or if you measure it for some while, you can also make it a bit faster by limiting the amount. So then you select which you want to detect, and then it just focuses on those selected VOCs. But how the final software will look, I cannot really tell you yet. It's still work in progress, but it can detect quite easily for us all the VOCs that we have in our library.
Okay, thanks a lot, Jan, for
Thank
your
you.
presentation and answers. So please, audience, you can post your question on the chat for Jan. And we move now to the following talk from Damien Bazin from Chromatotech. Damien, are you online?
Yes, can you hear me?
Yes, it's you, Damien.
So, yeah, Damien is not available today, so we make the presentation in his place.
No problem. So the floor is yours.
C'est là.
That's okay.
Okay, so good morning, everyone. My name is Mathilde Mascle, and I am a research engineer at Chromatotech. I will talk about laboratory and field validation at the Puy-de-Dôme research station of 2 systems for light OVOC measurement. So the European Union released a list of recommended molecules that should be measured to analyze trends in ozone precursors. This list includes molecules from various chemical families, such as alcohols, aldehydes, alkenes, terpenes, and others. And the analysis of such a diversity of molecules is an analytical challenge. The molecules of interest from the EU directive are shown here. Chromatotech Air Boson system is already able to analyze the majority of the molecule using 2 automatic GCFID, one for the molecules containing 2 to 6 carbon atoms, and the other for the molecules containing 6 to 12 carbon atoms. However, the molecules in red here cannot be analyzed by such system. These molecules are all oxygenated compounds and are more difficult to analyze mainly for 2 reasons. They are all light compounds with 1 to 3 carbon atoms, and they are reactive compounds. That is why Chromatotech has focused on these molecules with 2 systems, the AMOF which is specifically designed for the analysis of formaldehyde, and the HERMO-OVOC, which focus on the other oxygenated compounds. The HERMO-OVOC is an auto TD-GC-FID that allows the separation of the light OVOCs. 3 columns are used for the separation that is shown here on the chromatogram. Apolar compounds elute first from the polar columns, as we can see on the chromatogram here on the left. And after that, the polar molecules of interest here elute without any interference from other molecules. The system was tested under laboratory conditions, and here are some results obtained. The stability of the system was studied on a standard gas mixture generated with certified permeation tubes. The graph here shows the evolution of the concentration over time. And as you can see here, the concentrations obtained are really stable. And all calculated RSDs are below 1% for 48 hours of analysis. And the linearity of the system was also tested and found satisfactory, with all correlation coefficients above 0.99. And finally, the analysis of PAMS cylinder showed no interference from the molecule of interest. The MOF is a microfluidic device specific to formaldehyde and based on the Hansch reaction. So formaldehyde present in the gaseous sample goes into a liquid reagent, and the liquid formaldehyde will react with acetylacetone to form the DDL compounds, which then can be detected by fluorescence. The MOF contains a patented sampling device. An auto-zero is realized at each cycle, and this is an advantage for measurement of trace level concentrations, where the signal difference between the baseline and the measure is very low, as you can see on the figure here. And this ensures that no negative concentrations are obtained, even for trace levels of formaldehyde. The MOF was tested under laboratory conditions. The linearity was tested in both dry and humid conditions. As you can see on the graph that represents the peak area as a function of the concentration. Both curves are almost identical, with a correlation coefficient above 0.99, and this shows the lack of humidity influence and the linearity of the system. Both HERMO-OVOC and HERMO-F were tested in real conditions during a field measurement campaign at the Puy de Dôme research station. The campaign took place from July to September 2024. Both systems were checked once a day with an analysis of certified permeation tubes. Samples were also collected on DNPH cartridge for HPLC UV analysis, which is the reference method for formaldehyde quantification. This figure shows the concentrations obtained for formaldehyde, acetone, ethanol, and methanol during the month of July. So this shows first that the systems were able to continuously measure trace level concentration of the analytes. And we can see that, as expected, the trends of the various molecules are quite similar. During the campaign, formaldehyde samples were collected on DNPH cartridge. These cartridges were then analyzed by HPLC UV, which is the reference method for formaldehyde quantification. The results are presented in the graph here, where you can see the dark blue points are the results of the MOF, and the light blue points are the results with the HPLC UV. And you can see that globally both results are in accordance with the RSD value below 30% in average. The analysis of light OVOC can be challenging because of the physicochemical properties of these compounds. Chromatotech developed and tested 2 systems for the analysis of formaldehyde with the HERMO-F, and another system, the HERMO-OVOC, for the analysis of the light OVOC. Both systems were tested in laboratory and in field conditions. The MOVOC is stable, linear, and allows the automatic and continuous measurement of the target compounds. And the system can be made autonomous with gas generators. As for the MOF, it is a patented microfluidic device specific to formaldehyde quantification, with an auto zero at each cycle to prevent negative results even at low concentrations. There is no impact of humidity, and the system shows a good linearity, and the results are in accordance with the reference HPLC method for formaldehyde quantification. Thank you for your attention.
Thanks a lot, Mathilde, for your presentation. A very, very short question. Were there other instruments other than DNPH and your instrument during this campaign in Putodome? I mean,
Yes.
PTRMS, for instance?
Yes, there was other instruments. There was other instrument. There was a Picaro CRDS, but it's not our data to share. And also,
okay, so you plan to have this comparison in short or midterm? I mean, okay.
And also, yes, we will share that. And from our company, there was also a C2C6. So,
okay.
And yeah, which results were not shown here. Yes.
Okay, thanks a lot. You have a general question on the chat, please. I leave you answer to this question because we have to move to the following talks. Yeah. Thanks a lot again.
Thank you.
Because the next talk is from yours. Are you connected? I cannot see.
We cannot see him in the chat on the participants list, Stefan. So perhaps
I can go to the following one.
Yeah, maybe we'll go to Mihai and give him some time. Maybe if he shows up, we can go afterwards.
Okay, thanks a lot. So, Mihai, are you online? Yes.
Yes, okay. I'm here.
I guess I pronounced well your name. So the floor is yours. You can share your screen. To be ready a little bit in advance.
Okay, there it is.
Okay, full screen. Yes, that's okay.
So, all looks well?
Yes, that's perfect. So
perfect.
You have 7 minutes.
Perfect. Thank you so much. Okay, so hi everyone. My name is Mihai Ciobanu. Thank you for joining my presentation today. And today I'll present the development and application of a new high-resolution platform for the measurement of aerosol precursor vapors using filters. And with a similar setup that AJ Jost was also going to present. So I'll be presenting it first then, here. So I will start with a little bit of the basics so everyone can get on the same page. So first is about new particle formation. So to understand why we measure aerosol precursors, we start with the sources, which can be both anthropogenic, like sulfur dioxide or ammonia, or biogenic, like VOCs or iodine. These trace gases undergo rapid oxidation and hydration reactions in the atmosphere, often involving water vapor, hydroxyl radicals, ozone, nitrate radicals, which then help them produce lower volatility products. These low volatility products allow them to cluster the low volatility, forming stable nuclei and eventually leading to aerosol particles through the process of new particle formation. Then these particles can increase the albedo, earth albedo, act as cloud condensation nuclei, or adversely affect human health. Thus, the aerosol precursors which lead to these aerosols link directly to both climate systems and public health, making their measurements critically important. So in this table, we now see from O'Donnell et al., we now see how they show measurements from models of organic matter concentration and atmospheric optical density were substantially underestimated when atmospheric processes stemming from aerosol precursors, in this case it was secondary organic aerosol formation, was not included in the model, and when aerosol precursors were considered, the performance was improved. Then multiple other studies have shown strong links between aerosols and pollution effects, reinforcing the importance of robust precursor measurements in policy and air quality management. However, current measurements face a few key challenges, which are that these aerosol precursor vapors happen to be at ultra-low concentrations, typically in the parts per trillion or parts per quadrillion in volume concentrations. And there are also measurements, ground-based measurements for these specific vapors in stations worldwide are sparsely allocated, not on a global scale. And they're also quite chemically reactive, giving them complex atmospheric dynamics. So to address these issues, we are characterizing now a new system capable of offline ultra-sensitive characterization, which consists of 3 different parts. It's a mass spectrometric system consisting of 3 different parts. One is a thermal desorption unit, which heats filter samples hosted in specific cassettes, simple filter samples, to release the absorbed vapors without the need for solvents. Next, the vapors are introduced into an inlet that supports different reagent ions, such as nitrate and uranium, so it can host multiple. And finally, the analytes are detected using an Orbitrap Exploris MX mass spectrometer operating at 180,000 resolving power, which is sufficient to separate isobaric species even at high mass-to-charge ratios. Combined, the system is referred to as the TD Meon Orbitrap, and the advantages that it provides is that it allows detection of aerosol precursor vapors down to parts per trillion volume or even parts per quadrillion in volume. It can resolve overlapping peaks in complex mixtures of ambient air. It works with portable filters, like I just said, enabling spatial coverage without in situ instrumentation, and it supports multiple ionization chemistries, improving the selectivities of different vapors. So the first use of this TD Meon Orbitrap system was done with filters that were collected from 2 different locations. One, a background mountainside in Cyprus, and another one, a boreal forest in Finland. A major difference between the 2 locations is the vegetation type and density. And in this field experiment, this difference was successfully captured by sampling hundreds of different highly oxygenated organic molecule species on the filters. And on average, the filters from the Finnish boreal side managed to capture more HOMS, so highly oxygenated organic molecules, compounds containing mostly, especially just here at the mass-to-charge ratio of 400 to 450. In this region lie compounds containing mostly 11 to 15 carbons, and this showcases the ability of this offline system to capture differences in emissions, fingerprints in these 2 different regions. Then, to further validate this method, at the same boreal forest site in Finland, online measurements of aerosol precursors were conducted utilizing nitrate chemical ionization with an Apitow mass spectrometer in the same location at the same time. The mass spectrometer was calibrated on site, and this allowed us to get diurnal concentrations of various vapors. So the online measurements we can see with a line plot, and the offline measurements from the Meon Orbitrap with the scatter plot. And with the help of online measurements, we confirmed that we could capture on our filters concentrations of sulfuric acid, that's red, methane sulfonic acid, green, and malonic acid in orange, down to parts per quadrillion in volume levels. In addition, we also observed different highly oxygenated organic molecule families from the filter measurements. Again, even during days when their concentrations were down to the parts per quadrillion in volume levels, we could see them on the filters as well. So to summarize, this is the first demonstrated use of filters for chemical ionization orbitrap-based measurements of aerosol precursors. We successfully measured multiple compounds classes, including HOMS and inorganic acid using nitrate chemical ionization strategies down to parts per quadrillion in volume levels. So next, we plan to expand these measurements to include amines and ammonia, which are also important precursors, and we're looking to calibrate the system itself using multiple calibrants to account also for compound filter interactions and improve quantifications. Thank you.
Thanks a lot for this presentation. I do not see any question on the chat. I have one question about how challenging is sampling in situ. What are the attention you have to pay attention when you sample the filter in situ? What kind of filter is it, and how you have to? What is the logistic for those filters? Just to have an idea of the sampling procedure, because it's really interesting. I understand that you can sample in different sites, in different sites, and then have this analysis with offline system, and it's really interesting. But how challenging is the sampling phase?
Yes, so the sampling phase actually is quite simple, as we don't do any preconditioning or any post-processing of the filters themselves. So to do let's say, field experiments with these filters, we use some just pumps, let's say, to draw air in through the cassettes, through the filters at specific volumetric flows. And to make them reproducible, we keep them for 24 hours to sample in a specific location. And again, to make them reproducible, so we always carry background filters as well, which get the same treatment, but don't get, they're not being sampled through. So they're kept in their containers, but carried in the same places to get like a travel background of the filters that they can be removed from the samples. And zero backgrounds as well. So the filters, after they're sampled, they're only inserted in the thermal desorption unit directly, as they are in their cassettes. And the heating that it provides with some flows is enough to desorb at least the compounds that we have found so far from the filters.
Okay, and what is the nature of the filter? Which kind of material you have for this filter?
Yes. So far we have only tested 10x coated filters, so polymer coated filters, which are supposed to be better for VOCs and volatile compounds and gases. Things like that, yes.
And connected to a question we have on the chat from Frank Moses. What is the flow rate of the sampling, or because you mentioned 24 hours of duration of the sampling,
yes.
But at which flow rate, just in order to have an idea of the sensitivity of the method, do you have an idea of this flow rate?
Yes, we keep the flow rate constant at 1 cubic meter per hour, which is standard. Yes.
Okay, and without any special inlet for this sampling? You have no inlet. I don't know, with a PM 1, 2.5 inlet.
No, without no special inlets. Or we're sampling, we're measuring everything that is captured. Yes.
Okay, just because this sampling phase is crucial for people to see the capacity we can have on the set. We have another question from Liselott Tinel. At what temperature? At what temperature do you disturb the filter? Do you expect to degrade some compounds at the desertion temperature?
Yes, we tried different temperatures, and now we're using them at we're desorbing them at 240 degrees Celsius. We tried higher and lower temperatures, and that 240 degrees seemed to keep most of the compounds that we were looking at least homes, inorganic acids. We could still measure them, so they were kept intact. They were not degrading.
Okay.
But not more. Yes. Thank you.
Okay. Thanks a lot for your presentation and for your answers. So please have a look on the chat, because Chromatotech put an update or complementary information. So thanks again to all the speakers. We got, except if is missing
HJ
person.
he's now online, so maybe he can go ahead.
Okay, so we can take this presentation. Yes. So yes, the floor is yours.
Hello, thanks everyone. Let me see the sharing.
Yes, you can share your screen.
So I'm gonna keep it short.
Okay, just put in full screen. Yes.
Do you see the full screen or the presenter?
Yes, that's okay.
All right. So I'm gonna talk to you about a new way of creating reagents in chemical reagent and chemical ionization mass spectrometry. And in the context of what we do is with multi-pressure chemical ionization. So we have a system that ionizes at multiple pressures, so at ambient pressure and at reduced pressures. So you get the whole coverage of VOCs and HOMs, bases and acids all in one system. But today I'm just going to focus on presenting you our updates on the urea. So generally, if you have a positive mode ambient pressure ionization, you have an issue with the stability of the supply. So like NH4 is one. You have issues with contamination in the system. So we want something that's safe to humans and not corrosive. Like aminium is corrosive. The nitrate, the nitric acid that you use for the nitrate chemistry is very nasty. With ammonium, you are very low in the mass range, so it's frequently very hard to actually get it covered in the mass spec. So having something at a higher mass is very convenient. Good proton affinity for positive mode is useful, and urea has other nice features. It has these exposed groups that then make it a very good chemical reagent. It attaches nicely, so has lots of advantages over traditional positive mode reagents. So how do we do it? Well, the problem is urea is a solid, so it's very hard to get into the vapor phase, and the amounts you can normally get off is not sufficient to be used in a ion source. However, if you put it in front of the X-ray directly, the urea pellets in front of the X-ray, and then in the muon source, we accelerate them against a counterflow. So there's also nothing else other than ions coming from the source into the IMR, for the ionization. Then it works. It's a beautiful source. It has contaminations of less than 0.5% in the total ion count, and just the monomer and the dimer are dominating the spectrum. And it's a very stable source. We've had only variations within plus minus 10% over many months now. The data here goes only December, but we keep it running, and we have not seen any deterioration of the system. So we start to think that actually the source may outlast the mass spectrometer. The main ionization mechanisms, there is the cluster formation, and the cluster formation from the dimer, and then you can also end up with a protonated analyte in some instances. It's actually a very nice interaction based on quantum chemical reactions. So it's kind of a locking mechanism between the urea molecule and the target molecules. We get a lot of very high sensitivities. If I want to focus here on the right side picture, so the LODs are in the parts per quadrillion range. This is based on 100 counts per second at least. And you see that there is some trend with binding enthalpy, but we get very good sensitivities for like pyridine, DMSO, TMA, and substances like that. But we also can detect ammonia with the system. And actually, we've done a comparison with the quantum cascade laser instrument just outside the window in Helsinki earlier this year. And you can see that the ammonia from the diode laser in blue and our ammonia track quite nicely. And on top of that, we also can detect the amines in sub-ppt quantities at the same time. So very powerful. So if you look at overall, if you combine a nitrate, uranium, and fluorantanium, so fluorantanium is the low pressure source we use. With the low pressure source, you get the VOCs, and then with uranium, it fills in nicely in the middle oxygenated states, and then the high oxygenation states you get with the nitrate chemistry. We actually also create the nitrate now out of a solid, so no more nitric acid needed. That's actually shown here. So we use ammonium nitrate for the nitrate source. Same with so it's also generated in front of the X-ray, and then we create the uranium in front of the X-ray, and the fluorantanium is created inside the Orbitrap at reduced pressure. So yeah, if you want to learn more, there's a paper, a preprint published in ChemArchive. So the key is we can desorb the urea straight from solids. It makes an attachment at ambient pressure, very efficient chemical ionization for moderately polar and lowly oxygenated and basic gases, and very stable source. So with that, I think I'll end my presentation.
Okay, thanks a lot. Unfortunately, we are a little bit late, so please ask your question on the chat. We haven't time for question anymore. So we got a very nice overview of new instrument capacity for a wide range of VOCs and other reactive gases. So thanks again to all the speakers. And now I give the floor to the organizer or the chair of the following session, Sindhu. Thanks a lot.
Great, many thanks, Stefan. And now we're moving to the next session on greenhouse and reactive gases with our chair, Dr. Sindhu Raj Parampil. So Sindhu, the floor is yours.
Thank you, Eleni. Good morning, everyone, and welcome to the session on greenhouse gases and reactive gases. So we can start, and just maybe I can give a quick overview of, if you're not familiar with ICOS, we are a European research infrastructure. We make long-term high precision measurements of carbon dioxide, methane, and nitrous oxide, and other few gases as well. And we are in around 180 stations in 16 countries. So, and the head office is in Helsinki, Finland. So without further ado, I think we can start. Apologies for any names that I may mispronounce. And perhaps for the audience, please add your questions in the comments as it says, and maybe you can add the name of the speaker whom you are addressing your question to, so that it'll be clear. So we go on to the first talk by Rubina Papakonstantino, a dual platform approach for quantifying methane emissions at site level. Rubina, the floor is yours. We don't hear you.
Hello, can you hear me?
Yes, please.
Can you see on the screen?
Yes, we can see your screen. You can put it on full presentation mode.
Okay, is it okay now?
Still, we're waiting.
Mm. What now?
No, still it's still in the slides mode, but perhaps
Don't know.
maybe one more try, and maybe otherwise we can worst case continue like this. It's okay. Maybe you want to try once more about this, and then we.
Now for me it's full screen, but I don't know why it's not working for you.
Okay. Yes, there seems to be a bit of delay in your voice as well. Perhaps switching off the camera would help make things a bit better.
Yes.
Yes, please go ahead. And 7 minutes.
So hello everyone. I'm going to present you our work on a dual platform approach for quantifying methane emissions at site level. So first of all, what is methane? It's a short-lived climate pollutant, and that means, as the term says, that they have a short lifespan and high potency, meaning that they are breaking down in the atmosphere faster than they are released, and this means that by reducing their rate of emissions will lead to a reduction of global warming in the near term, even if the emissions are net positive. So the methane has a global warming potential 28 times greater than CO2 over 100-year time span, and it can also improve the local air quality by reducing also tropospheric ozone.
Sorry, Rubina, I'm sorry to interrupt, but we don't see your slides changing. I don't know if I'm not the only one.
Really?
No, we don't see your slides changing. Yes, now, please.
Now, okay. So as I was saying, it can also improve local air quality by reducing tropospheric ozone, which methane helps to produce. Some of the main sources of methane is agriculture, wetlands, fossil fuel production, landfills, etc. But in order to be able to tackle these emissions, first of all, we need to geolocate them. And that's why we organized the Gochadis campaign, which took place earlier this year. The aim of this campaign was the field demonstration and benchmarking of this state-of-the-art dual methane platform system to geolocate and accurately quantify emissions from Gochadis landfill, which is a landfill 20 minutes away from the capital, Nicosia. You can see here a map and a more zoom in figure of the landfill. I want to mention here that the landfill is inactive since 2018. A short introduction to the dual platform. As you can see here, and by that I mean that we simultaneously use the car and a drone platform to better capture the 3D reconstruction of the methane plume. So for the car, we used the AirMar weather station on top of it, as you can see in this figure, and the Mira Ultra Mobile LDS for the methane measurements. As for the drone, we used the GPS and the ultrasonic anemometer on board. And for the methane measurements, we used the ABB Los Gatos research. The methodology for contacting the measurements for the car, it was driven along roads that were adjacent to the landfill site, as you can see in this short schematic, always downwind of the source and perpendicular to the wind direction. The UAV flight plan was performing horizontal transects, again downwind of the source, at various altitudes, as you can see here, starting from low to high altitudes, perpendicular to the wind direction again, and creating the so-called curtain measurements To estimate the emissions for the UAV platform, we use the mass balance box modeling, while for the IRIS car-based measurements, we use the Gaussian plume inversion model. I'm not going to go into details on the specific equation used for these models. So moving on directly to the results. The total days of the campaign were 10. We managed to perform a total of 60 UAV flights and 122 useful car transects. You can see an example of a case study in this map here. With the yellow circle, you can see the UAV track. As said before, we did the so-called curtain flights. And the data points are colored with regards to the methane concentration. And as you can see, these data were then interpolated to the plane perpendicular to the wind direction so as to be able to calculate the estimated emissions. On the red circle, you can see a typical car transect performed during the campaign. And on this figure here, then down right, you see the observed peak, concentration peak, and the model Gaussian model concentration. And I would like to note here that the estimated flux from the UAV was about 100 kilograms per hour, while from the car around 2000. And you can see how big this difference is, even if the platforms were running at the same time and capturing the exact same plume. So you can see here the sum of the 10 days of the campaign. And again, you can see with red color, the car IRIS estimations of methane flux, and with blue, the UAV Los Gatos research estimation of fluxes. They're having at least one order of magnitude difference, and this is very significant because we are having a bit of struggle to explain this, but I guess this is part of science. These discrepancies from the instrumental part are unlikely because both systems have thoroughly been tested in the past. So it is possible that this difference is due to the spatial variability of the source or the presence of multiple emission points in the landfill. So more detailed 3D mapping of the area will be needed in the future. Another reasoning behind this huge difference might be the complex terrain of the landfill area that might influence how the plume is dispersed in the whole space. So to conclude with, we have integrated a car and drone-based mapping that enabled us to see the 3D plume characterization and provide an enhanced sampling and more precise quantification estimates. And this framework is very interesting and advantageous for such sources that are diverse and more complex to capture in terms of topographical factors that influence a lot the methane behavior. And with that, I would like to thank you for your attention, and I'm happy to answer any of your questions.
Thank you, Rubina. I don't see any questions yet, but I was wondering, is this the first time this dual approach has been used, or have you attempted this elsewhere?
From what I know, this is the first time that such a thing happens. Usually people are using these platforms independently, so either drone or either mobile platforms or stable ground platforms, but this combination is something groundbreaking, and this is the state of the art of this work.
Yes, it's very interesting indeed. Do you have any thoughts on how you would proceed with trying to maybe better understand, the difference between the quantifications in the two approaches?
Mm-hmm. yes, it's in the plan to continue these flights and mobile measurements in the landfill. And the plan is to do it at the exact same distance from the source, so having the drone flying just above the car so as to be sure that they are capturing in the same terrain, in the same, let's say, latitude and longitude. So no difference in the spatial term, let's say. And that maybe gives us a more certain answer of this huge difference.
Right. Yes. So all the best for that, and hopefully we will hear more from you at some point. But thank you. Keep an eye out for the chat. There are no questions yet, but perhaps somebody might have something to ask you. So thank you, Ravina, and we move on to the next speaker. So we have Jonas Brookhusen, who will talk about a new all-in-one instrument for air quality and greenhouse gas monitoring. Jonas, are you there?
Yes, I'm here. I'm just trying to share my screen and get my camera, but somehow the browser is not allowing this. Wait, okay, maybe like this. Hope you can see my screen now. Maybe now.
Coming.
Can you see it? Is it there?
Yes,
all
it's
right,
there.
perfect,
Yes.
great.
Yes.
I think my camera is still not working.
No,
right?
we can see you as well. Yes.
Oh, perfect. Okay,
Yes.
then I
Please.
think I'm good
Welcome.
to go.
Yes.
All right, perfect. Yeah, okay, great. Yeah, so thank you very much for having me here today. I'm Jonas, I'm application scientist at Miro, and it's a nice opportunity to present our new all-in-one gas analyzer for air quality and greenhouse gas monitoring. And so for those who don't know us, we are Miro. We are a young company from Switzerland with our purpose empowering the world to combat climate change and air pollutions. And since October 23, we are now part of the Bruker Group. And even though we are a rather young company, we already have several dozens of analyzers on the field across 3 countries operated by some of the most prestigious labs, as you can see down here. And so our approach is to provide our multi-gas analyzer. So it's basically an instrument that can measure from 1 up to 10 different gases, depending on how it's customized for our customers' needs. And so we can measure up to 10 different gases simultaneously. All gases are measured directly with high precision, ideal for trace gas monitoring and ambient air applications with high time resolution, so 10 Hertz, and no sample treatment is required. Here you can see just the in total 13 gases we are measuring. So you can choose basically 1 to 10 gases from this list combined in one instrument. Not all combinations are possible, but most of them. And so as you can see with this precision, this 1 second precisions listed here, usually we have PPT or single digit ppb precisions for all compounds, making this ideal for ambient air applications. And so what happened during the last 1 or 2 years, we implemented several new functions, and I would like to show you a few more things, like how we are constantly improving our instrument. The first thing is a real-time water vapor correction for greenhouse gases. So this was constantly requested by the community. And so now we have this function accounting for both important effects, the dilution effect. I think this is kind of straightforward, but there is also a spectroscopic effect. So each absorption line is broadened by the water vapor. And so we need to account this for each gas and each absorption line individually. And so with our new automatic function, we are doing this. And as you can see here for some greenhouse gas examples, by just varying the humidity or the water concentration while measuring a gas standard, we get very stable and constant dry concentrations for our gas standard. A second thing we implemented is an accurate timestamp. And this makes especially the synchronization or the combination of the analyzer with other instruments way more convenient. And so our analyzer can receive now NTP timestamps either from the internet or via a GPS antenna, and actually can switch between these two sources depending on which one is providing the more accurate timestamp. And this is, of course, interesting if you combine instruments. And so for our eddy covariance customers, we even went one step further. So with our partners from METEC, we implemented now a trigger signal coming from our gas analyzer to combine or to trigger the anemometer, providing the wind data. And with this, you get perfectly synchronized gas and wind data, which makes the data post-processing or treatment way more convenient when not even unnecessary for the eddy covariance approach. And so how can this be used, or how has our analyzer been used lately or in general? Here are some examples I would like to show you. So the first one is, of course, eddy covariance, because this is one of our key applications. And I choose an example of Nina Buchmann from the ETH Grassland Science Group in Zurich. And so they do eddy covariance measurements at their site in Lägeren in Switzerland, but they are not just measuring greenhouse gases like CO2 or N2O, but they also do eddy covariance on OCS, which can be used as a tracer for CO2 because it is uptaken the same way by the vegetation as CO2 does, but it's way more simple. And so this shows that with our analyzer, you can go beyond the standard greenhouse gas eddy covariance, because in theory, you can do eddy covariance on all 10 gases. Another nice example, or a very important application for us, are mobile measurements. And so we have plenty of customers driving and especially flying with our instrument. But here I just choose an example we did ourselves. So you can see that we turned actually the ordinary station wagon of my colleague into a mobile lab by just integrating our gas analyzer. And then we were driving through the city of Zurich, chasing some emission sources and high pollutant areas. The last example I would like to show you is actually more kind of a new product. It's our MGA-I. It's an N2O isotopic gas analyzer. And this analyzer is ideal to decipher the geochemical cycle of N2O. This is especially interesting for N2O because we have these two isotopologues right here, which have the very same mass. So they cannot be distinguished by mass spectrometry, but our low vibrational spectroscopy can distinguish them clearly. And this is very important for source emission signature tracing, and helps a lot to understand these processes. And so here are just some examples, or like the performance of this analyzer for pre-concentrated N2O or higher concentrated N2O. And you can see that we can measure up to 5 different isotopologues, even this 17O, and we have precisions of better than 0.5 or even 0.05 in these cases. And yeah, with this, I would like to conclude and summarize. Miro Analytical provides a gas analyzer that can measure up to 10 different gases at 10 Hertz time resolution. We often achieve PPT level of precision and have high stability. With our isotopic analyzer, we can measure up to 5 isotopologues of N2O, and this can be used for mobile, especially airborne monitoring, for monitoring station applications, or for the eddy covariance approach. Thank you very much.
Thank you, Jonas. There is a question for you from Shmuel. He asks how this all-in-one instrument can support in practicing reduction of greenhouse gases and polluting emissions. Do you have any thoughts?
Yeah, we always say you cannot handle or you cannot manage what you cannot see or what you cannot measure. And so I think especially this multi-gas approach is very interesting to not just get information, let's say, for instance, about CO2, but all the processes related to it. And so I think there is a very interesting project just finishing the ICO Cities project where they measure greenhouse gases in urban environment. But with our instrument, they were able to measure also reactive gases like CO and NOx, for instance, and learn more about the sources and the processes related to the greenhouse gases. So I hope this answers the question.
Indeed, thank you. So this the 10 the mirror which does the 10 gases, do you have these in several places, or do you have a feel for the number of sites that are using these, or is it very, very new?
No, let's say for this measuring stations, usually not all 10 gases are chosen because often people already have existing analyzers. So a lot of our eddy covariance customers, for instance, choose only greenhouse gases, but especially the mobile application, they really benefit from this 10 gas analyzers. So I would say roughly 50% of our instruments are 10 gas analyzers, but then it's often mobile applications or very versatile applications, of course, because you can use it for different approaches.
Yes, I agree. Thank you. Thank you for a very nice. Okay, there is one question for you now. I think we can quickly take that and move on to the next question. So, Guido asks, which is the environmental pressure range of correct working of the instrument? Do you have an algorithm for the overpressure correction?
So we work at reduced pressure to just narrow down the line width. We can handle maybe a little of overpressure if the flow is low, but usually we are actually limited to ambient pressure. Going to lower pressure might be possible, but then we lose sampling rate. But ideally we work at ambient pressure.
Thank you so much, Jonas. And now we will move on in the interest of time to our next speaker. Thank you very much for a nice presentation. So next up, we have Magdalena Hoffman, who will talk about ammonia monitoring and meeting the new EU air quality directive with the Picaro and Permacal systems. Magdalena, the floor is yours.
Yes, thank you. Okay.
We see your slides.
Okay, perfect. So I am Magdalena. I'm a senior application scientist working at Picaro, and I will be talking about ammonia and both about our new ammonia analyzer, the PI2103, and a new device available from LNI Swiss Gas, which is called Permacal, which allows you to calibrate our analyzer. So some background on ammonia monitoring and the new EU air quality directive. Well, ammonia is a hazardous air pollutant. It significantly impacts human health and ecosystems. And one of the major sources are agriculture activities like fertilizers and livestock emissions. Now, this is, there is a general because of the importance of ammonia as an air pollutant, this is picked up by the new EU Air Quality Directive, which is calling for more ammonia monitoring, both in urban and rural settings. And of course, it also emphasizes the importance of reliable measurement methods and robust calibration protocols. So while it's very important to monitor ammonia in air, there are some challenges. Most importantly, ammonia is very reactive and it also absorbs to surfaces. And on the other hand, there is a lack of stable and calibration gases, which makes it very difficult to calibrate ammonia analyzers, or which can make it very difficult. And this is here we'll present you two solutions today. So yeah, we have a new ammonia analyzer, which is called PI 2103. It is a combination of the two previous models, which were called SI 2103 and G 2103. The G analyzer has already been used for atmospheric monitoring since years, and the SI 2103 was our analyzer, which was specifically developed for the semiconductor industry. Now we combined the two previous versions, the G and the SI version, into the PI 2103, which is kind of picks up the best of the two existing or previous ammonia analyzers, which means it has the fast measurement rate from the G 2103, but also the more stable Linux platform and an upgraded sample handling. In terms of performance, you can expect the same excellent performance that you might already have seen from the G version. So we are talking about PPT precision and virtually no drift, so less than 0.5 ppb drift per month. And the analyzer spans a large concentration range. It can measure up to 50 ppm with the extended range. And it is also optimized for handling sticky gases, which means it has a very short response time. We're talking about less than 1 minute for when testing an increase from 0 to 20 ppb ammonia. Now here, this is that's a table from our data sheet. And here I just quickly want to highlight, we generally make a distinction between our specifications. This is what we guarantee, and the typical performance. And the typical performance refers to the median of the last, let's say, 50 analyzers that we built. And I just want to comment here that in general, our typical performance is about a factor 3 better than the specifications for this specific ammonia analyzer. Now, my presentation here today is mainly to talk a bit more about how do you validate the analyzer, right? And there are essentially two options. Option one is that you verify the linearity of the analyzer using CO2 as a surrogate gas. And that's important to note that while the analyzer measures ammonia and water vapor, it also measures CO2. And the option two is that you can make use of this new permacal device from LNI Swissgas, which allows you to validate the analyzer directly using ammonia. Now, option one. So for the surrogate gas validation, that's something where we suggest to do this on a monthly to yearly basis. And the advantage is that carbon dioxide is non-reactive, it is easily commercially available, and it has an absorption spectrum close to ammonia, which means if you verify the linearity with CO2 gases, you can be sure that the analyzer will also behave linear for ammonia. And obviously this avoids then the common issues that you might have with ammonia calibration standards with respect to absorption and stability. So this is an approach we have been promoting already since a few years. However, the new EU Air Quality Directive is asking to validate the species of interest directly, to validate ammonia analyzers directly with ammonia. And therefore, I just want to also present to you the second option, which is this LNI permacal device. So the permacal device allows you to generate ammonia in situ using a permeation tube. And the concentration is precisely controlled by the permeation rate, the carrier gas flow, but also the oven temperature. And this system was developed by LNI Swissgas in collaboration with METAS in Switzerland. Now, some of the key features is flexibility. You can set any target concentration between 15 and 150 ppb. with a single permeation tube. It is a portable system, so it's actually available in 2 versions, and there is a portable system which has a battery and a charger which allows you to do the validation directly on site. And it is also coated with Silconert to have a very good response time when dealing with the sticky gas. Now, for those of you who are less familiar with permeation tube, just a quick schematic here of how it looks inside of the permacal device. There's a Teflon tube, which is hosting ammonia in the liquid phase and also in the gaseous phase. So there's an equilibrium. And then you can heat the temperature. You can heat the Teflon tube to a certain constant temperature. And that's how you can change the gaseous phase, the concentration in the gaseous phase. And that's then when the gaseous ammonia is diffusing out of the membrane. So the concentration is determined by, well, obviously by the type of the permeation tube, by the carrier, the flow rate of the carrier gas, in this case 0 air, and also the temperature of the oven. Now, here, this is just to give you an idea how it can look like when you do validate an analyzer using this LNI permacal device. Here we tested a PI 2103 and a G 2103 in the range of going from 0, measuring the 0 from the 0 air up to about 40 ppb, and you can see that both systems showed an excellent linearity, so the slope was very close to 1, so 1.009 and 1.003. Okay, so just to conclude, this new air quality directive is asking for more comprehensive urban and rural ammonia measurements. The PI 2103 is an ideal solution to monitor ammonia close to the source, but also at background levels. And the LNI permacal device aligns well with the EU directive in that sense that you can calibrate the analyzer directly using ammonia. And that's it. In case you do have any questions, then please don't hesitate to reach out either to us, so info@picaro.com, or directly to LNI Swissgas.
Thank you, Magdalena. Very promising instrument, and it looks very interesting. I may have missed this while you were speaking, but how, the data that you showed, was this out from the field, or was these laboratory tests that was done?
That was actually done during a training, so in kind of a lab environment with two analyzers. It was not in the field, but it was not directly a lab environment. Well, it was a normal office space where we did the tests.
Right. Is it already available or have people already started testing it in the fields or in stations?
Yeah, it's definitely available. I'm aware that, well, I know that it's been used by some customers already in France. I'm not sure if it was really used at the monitoring stations. I have Thomas from LNI. I think he should be still listening in here, so maybe he can comment on if the device was already used at monitoring sites. But I believe so.
Okay, good to know.
Yeah.
I don't see any questions in the chat yet, but please do keep an eye out for it in case somebody thinks of something. But thank you so much for a very interesting talk.
Yeah, thanks.
All right, then we move on to the last, but definitely not the least talk in this session. So it's...
Sorry to interrupt you, Sindhu.
Yes?
There was a last-minute cancellation, and unfortunately, Victoria Pelli will not be able to present.
Okay.
So, and we are just about, actually, in terms of time, is also break time. So,
all right. So
we will continue with the short break, a 10-minute break, and we will be back in 10 minutes for the next session. Thank you so much for chairing this session.
Yes, thank you. And thank you to all the speakers as well.
Thank you. Okay, welcome back, everyone. We will continue with our next session, which is on international initiatives, and it will be presented by Dr. Niku Kivekas. So, Niku, the floor is yours.
Thank you very much. So, good morning, everyone. Welcome back from the coffee break. And this session, we have 3 different presentations. First one by Päivi Haapanala on the climate risk research through research infrastructure services. Then by Franco Marenko on the DUST doctoral network. And the third one by Jeroen van Gent on the Kaleoscope product added value atmospheric products. So we are not talking that much about instruments. We are now looking for different and innovative and new ways to work with the data and work with the instruments for the added value. So this session, we have only half an hour. The talks are 7 minutes talk plus 3 minutes for questions. So if you are over the 10 minutes, we will just need to interrupt you. But without further ado, let's go to the first presentation by Päivi Haapanala. Päivi, the floor is yours.
Thank you. Are you already seeing the slides?
Yes, we are, and we hear you well.
Good. Yes, first, thank you for this opportunity to present our IRIS project in this interesting meeting. I'm Päivi Haapanala. I work at the Natural Resources Institute Finland, LUKE. And to get you on the right mode after the coffee break and the morning session, I give you a few seconds time to think about climate risk. What is the first thing that comes into your mind about climate risk or climate change-driven risk? Yes, I guess we all know about climate change and what kind of risks it poses are in the news all the time. And what in this IRIS project we mean with the climate risk. So we use this kind of risk propeller definition for the risk. So the risk is composed of exposure, vulnerability, and hazard. And in our project, we concentrate on climate change-driven risks. And as you can think, it's not easy to make this kind of research. So we need a lot of different kind of measurements or data or tools to get a holistic understanding of some climate risk in some spatial temporal location. So this IRIS is a project that brings together 14 national and international research infrastructures. It's a EU-funded Horizon project from this kind of infrastructure projects. We have in total almost 80 partners contributing to this initiative to our project. The project started a year ago and it's still running for another 3.5 years or a little over 3 more years. And here you can see in the slides the research infrastructures or the logos of the research infrastructures are part of our project. So perhaps some of them you are familiar with Actris and IGOS and IAGOS, which are also part of this workshop. But we do have other fields than only environmental. We also have health-related, social sciences, and e-infrastructures included in our project. And one of the main tasks, what we are doing or what's the aim of this project is to provide sponsored access, virtual access, and transnational access related to climate risks. So as said, there are 14 research infrastructures providing this access to these services, and there are facilities, over 18 facilities or platforms or installation all over Europe. And how you can find these services that these research infrastructures are providing, we have a catalog of services that brings together all the information or the services. There's different kind of search functions that you can use. Here in this screenshot, I have used a few of the examples from the research infrastructures, what kind of services or installations they are providing and what kind of access they provide into their services. So this is kind of our one-stop shop for finding the services related to climate change risks. And we offer access to these services. There are virtual access provided by different research infrastructures, and those are free to use at whatever time. And then there's this transnational access that is kind of physical access to a facility or the tools they offer. And for those, we have dedicated calls and there's a user selection. So if you have in your mind a climate risk related topic and you would need data or visit for some installation or platform, iRisk might be a solution for you. So we have these calls coming, the first one closing already in the end of this month, but no worries. There will be 5 other calls during the upcoming 2 years. And the idea is that we offer these services for projects that deal with climate risks. And we support multi-inter and transdisciplinary research in our project. So this is kind of like introducing you that we have these calls that you can apply and you can advertise them for your colleagues that we have these services coming. Currently, the services are those that are already provided by the research infrastructures, but later during the course of the project, there will become new services that are more targeted to special cases and are like collaborated together with the research infrastructures. And with this, I summarize that these iRisk projects brings together national and international research infrastructures that are providing services related or relevant for climate risk research. And we do integrate also the RI services, harmonize their service and access policies, and we also create new services during this project. And this is in short what iRisk project is about, and I hope that you will use our services or advertise them for potential climate risk researchers. Thank you.
Thanks. There is now time for some questions. Does anyone have any questions? I see no hands, so I will use my own. I have a question that what do you see as the main benefit of this project to the instrument manufacturers?
Benefit for instrument manufacturers? I guess they could use bring their instruments to some facility and do some comparison perhaps with other instruments that are already used in that facility. So that's the first thing that comes into my mind, that it could be used, those platforms, as a test places for their instruments.
Yes, so a message to all the instrument providers that this is a good way to test whatever the field is, since this is a multi-RI project with a plethora of different facilities. Any other questions?
Of course, the project needs to be somehow linked to climate risk, so you might need to take a little like a wider look and not just say that, okay, my instrument measures this, but how could it be used or linked to climate risk?
Yes. Any other questions? I don't see any. Therefore, I thank Päivi for this presentation.
Thank
we
you.
will go for the next one, the DUST Doctoral Network, presented by Franco Marenko from the Cyprus Institute, Cyprus.
Hello, thank you very much for having me here. Can you hear me?
Yes, we can.
And can you see my slides?
Yes, we can.
Let me try to put them in full screen mode. Yes, they should be in full screen mode.
Now they are.
Okay, Okay, so thank you very much for having me here. I'm glad to present to you the Dust Electron Network, which is a new initiative that is starting now. It is a project funded by the European Union and also by the National Agency of the UK and Switzerland for the part that is developed in those countries. I'm presenting here on behalf of myself and all the partners on the projects, which you can see here on the screen. I will not go through them one by one because otherwise the 7 minutes will just be stuck on this slide. But we have two categories of partners, what we call the leading partners on the left-hand side, there is 8 of them, and what we call the associated partners that you can see on the right-hand side, and there's 15 of them. The main difference, all the partners are equally important. The main difference is that the leading partners will hire a number of doctoral candidates to do the project, and so they will pay the salary, let's say so, and the other partners will contribute, but without employing the PhD students. If I put the partners on the map, maybe it gives you a better idea. We have a big nucleus in, let's say, Central and Western Europe, with a tail that you can see on the bottom right, going through via Greece, Cyprus, and the United Arab Emirates. And Cyprus is the coordinator. The Cyprus Institute is a coordinator of the project, which I represent. So why are we interested in dust? It's dust. Well, I want to remind what we intend by dust in this project is dust coming from the desert area. So it's soil particles lifted by the wind. Some other definitions exist of dust, but this is the one what we consider. So dust is emitted in the desert areas by the winds. It's advected also by the winds, and it can travel several thousands of kilometers. It can go, for example, from the Sahara all the way to South America, or from the Middle East all the way to Northern Europe. And during this travel, it stays in the air for a long time, and it undergoes a number of processes. The most obvious ones are the direct forcing of the radiation with scattering and absorption, and the interaction with the hydrological cycle when they act as cloud condensation nuclei and ice nuclei. Then the dust at some point falls back down to the ground or to the ocean, and it has an impact there as well in the oceans as a nutrient for the food chain, and in the on the surface it has an effect directly on human activities, on health. That's the most obvious one, but also, for instance, imagine energy production with solar energy is heavily affected by dust as well. Now, dust, what do we understand of dust? We don't understand so much, actually. Until a couple of decades ago, the main thinking was that all particles in the atmosphere are smaller than 10 microns, and therefore we built instruments that could not see particles bigger than that. And we also developed models that could not account for particles bigger than that, and therefore we kept in that loop of thinking. And then the evidence came out of these larger particles, and this is a new topic, but it's already not so new. It's already a few decades. But if the particles are the particle size is not so well known, you can imagine the particle shape. The particle shape is very irregular because we're talking about solid particles. And how do we deal with these irregular particles? We have quite a number of projects in the sub-projects of the DustDN that deal with this. And then if the particle size and shape are known, you can imagine what we know about the composition. Of course, we know generally that we have minerals from the soil, but depending on the source regions, their combination is going to be different, and this will have different properties. For instance, we know all that hematite is very absorbing, so the presence of hematite or not in dust will change a lot of the optical properties, and the densities will be different, and so on. Now, on the other hand, when we deal with satellite observations or models, we often assume a uniform dust composition, a uniform density, and so on. So this is something also we're going to research. To make this research, we will make use of a number of unique facilities that the partners in the project have, And I will again not go through them one by one, but we have a number of high-performance computing facilities. We have drone facilities at our institute. We have a number of ground-based observation facilities, whether in situ or remote sensing or both. We have an electron microscope center. We have a particle settling laboratory where we can model. We can actually model, but not a numerical model, a physical model of how the particles behave in a fluid. We have a number of solar radiation facilities, and we have also a couple of biochemistry labs where we will study the effect of dust on the health. And beside these facilities, we will make use of novel space missions, of which we as project partners are part of the science teams or calibration and validation teams. And therefore, yes, we will exploit these new missions as well for the study of dust. So we have 4 research objectives. One is the understanding the fundamentals of dust. The second one is to identify the influence of source regions on the properties, which I mentioned in the previous slides. We have a third one to discuss the socio-economic impacts of dust, and the fourth one is about dust in the global climate system. And these research objectives translate directly into work packages of the project itself. And under each work package, we have a number of PhD projects. For instance, this is the first of these research objectives, and we have 5 PhD projects. Again, I cannot go through them one by one, unfortunately. The time is a tyrant. But yes, these are the 5 on the first research objective. Then we have 4 on the second research objective. We have 4 also on the third and on the fourth research objectives. So what is the project status? The project started officially in November, but actually we started selecting doctoral candidates even before the official start. And now we're in the process of hiring them. 6 doctoral candidates have already started. Actually, in Cyprus, we also had the first campaign, which has been concluded. The 4 candidates are expected to start before the summer and 7 just after the summer. And so all in all, we will have 17 visionary PhD projects. So when I say visionary, I mean that we're going outside the comfort zones of things that we already do. We will try new things. And the project will enhance the potential of the unique techniques and facilities that the partners institutes have, and will further develop the synergies between the partner institutes. And we will advance, at least that's what we all hope, the science of dust in a significant way. But the most important, because this is a scientific but also educational project, it will train the dust experts of tomorrow that will be here presenting the next project maybe in a few years' time. So this concludes our presentation. Feel free to follow us. We have a beautiful website, and we also have a number of short videos on YouTube that you can watch and that present the project and the partners. And we also have a number of social media accounts. So yes, we are inviting you to follow the project. And that's all. I thank you very much for listening, and I'll be happy to take your questions.
Thank you. We have time for approximately 1 question. So is there anyone who wants to be the one? I don't see any hands. Therefore, I will first remind every instrument manufacturer that please check that your instruments and assumptions allow for particles larger than 10 micrometers. And really, it's not a question, it's a comment. I really like this approach that you have like a number of clear PhD projects within this project, and you are training the experts of tomorrow. I really like this approach.
Thank you for it. Actually, this is the doctoral networks are a specific call of the Marie Curie actions of the European Union that is encouraging to have this approach. Yes.
Thanks. Then let's go to the next presentation.
Thank you very much.
That shall be by Jeroen van Gent from Bira in Belgium about the kaleidoscope.
Yes, can you hear me? And can you please?
We can hear you, and we currently see the program.
Yeah, that's correct. Can you also share my video? Because I'm not allowed to share my video, it says.
We're not allowed to share.
Well, it says if I click, I try to activate my camera, but it says that the host blocked it. So maybe you can activate.
The host, that would be Eleni, probably. So I think.
Yeah, we haven't blocked anything. So let me just check if we can, if I send you a request to maybe activate your camera again.
So I
Okay,
think it
now we
should
can
be.
see you.
Oh,
Yeah,
okay,
now we can
perfect.
see you.
Now we can see you.
Okay, perfect. Hopefully you also see my presentation now.
Yes, not yet in the full screen mode. Now
okay.
It is.
Okay, perfect. Okay, thank you for having me today. My name is Jeroen van Gent from the Royal Belgian Institute for Space Aeronomy in Brussels. And today I'd like to talk to you about two things. First of all, an online working environment that's called Terrascope, and a project activity that's called Kaloscope. The two are related, and this is from a satellite measurement point of view, so a bit of an outlier maybe in today's community, but I hope to convince you in the next couple of minutes of the link. So first of all, a slide that I kindly received from my colleague Jürgen Everhard from the Flemish Institute of Technological Research, who is the head of the Terrascope platform. What is Terrascope? It's an online working environment, a full ecosystem, if you like. It's actually an initiative from the Belgium Federal Research level. First of all, there is a viewer. Let me activate the pointer. Yes, so there is a viewer. If you go to the website, you can watch a lot of different satellite data sets. And but it's much more than that. So behind it is a full cloud processing system, and you can get a virtual machine there and do your own analysis of the available data and bring your own data sets in there as well. Of course, you can download everything that's available. And if you don't want to work on the system directly, you can also use this so-called OGC web services, where you, for example, can integrate the satellite data in your own GIS systems. And there's an API behind it that links all the different components. And this API lives up to the OpenEO standard, so it should be relatively easy for you to work with. Important, there are many thousands of subscribed participants already, subscribed users, and everything is available for free if you don't overdo it, of course, if you don't calculate at unreasonable levels, everything is available for free. So a more formal name of Terrascope is that it is an ESA Copernicus Belgium collaborative ground segment. It's a mouthful, but it means that as a ESA member state, Belgium and other member states have the capability to create such a system. It can be in many different forms, where we offer satellite products that are thought of added value to the user community. So not the usual operational products that are available elsewhere, but things that go a little step further. At the moment, it hosts a wide variety of satellite data sets from the Copernicus Sentinel series, Sentinel 1, 2, and 3, which are mostly images of the Earth's surface. And in our activities here in Brussels, we focus on the Sentinel 5P trace gas column data. On the right, you see an image of NO2 signal, a map over Eastern Asia. And it is available in different varieties, so as daily, monthly, and yearly maps. One thing to realize is that most atmospheric measurements from satellite provide actually a total vertical column of some altitude range. So not the surface concentration directly, but the total column from the ground to the top of atmosphere. So this Sentinel-5P Tropomi satellite, for those of you who are not familiar with the system, it was launched in 2017. And for the atmospheric satellite community, it was really a revolutionary step in the sense that it proved to be very sensitive. And most of all, it has a very high, well, in our terms, a very high spatial resolution of about 3 by 5 kilometer ground pixel. That may not sound much if you want to do local measurements, but for satellite atmospheric composition measurements, it's quite a big step forward. And as you can see by this average map, averaged over a couple of months over Europe, you really can see all the smaller communities and cities and towns in the NO2 signal, and you can even see some shipping tracks over the Atlantic and the Mediterranean. So this was really a really nice satellite to have, and it still is. So like I said, I'm working at an institute in Brussels. As an institute, we have been strongly involved in the S5P Tropomi mission since the very beginning in 2017. And over the last couple of years, we cooperated with Vito to implement the first products for Sentinel-5P in Terrascope as daily, monthly, and yearly averages. These are the products that are already available in the system. So we have formaldehyde, that is one of the VOCs that is a good indication of both natural and anthropogenic activities. There is carbon monoxide, there is NO2, a lot of pollution here shown over Eastern Asia. There is Cobra SO2. Cobra is an algorithm type that was developed here at our institute, and which is actually an additional step, an improved version of the SO2 algorithm that is in the operational ground system for the S5P satellites. And then maybe the most important thing for today is that we now also have a first surface NO2 product, so a surface concentration. Because like I said, most satellite products typically provide a vertical column, which is not directly a quantity that is useful to different user communities. Because, for example, the average person is interested in the air quality at ground level, and therefore surface NO2 is a much more relevant factor. One I didn't show yet is methane. I just show it here in this way because the Terrascope environment also allows you to compare concentrations and quantities for different time frames. Just this image as an illustration of that. Okay, so Kaloscope, that's a project activity related to Terrascope. We were very lucky to have further support from the Belgium Science Policy organization to further develop S5P projects for Terrascope. But here we really wanted to further dig into this extra step towards the community of users, health bodies, and scientists that are interested in measuring air quality at ground level. So we want to further develop machine learning techniques that provide that use satellite data as input, but provide in the end surface concentration. So we think of scientists, but also health authorities, policymakers, even the agricultural sector, and maybe you today you see the link with what you are doing at the moment. I already mentioned this first NO2 product that we have in the system. As input, it uses the Tropomi satellite data, but also some auxiliary data sets, more like meteorology, like from ECMWF, ERA5 land data parameters, traffic and road network data, and a few others. There's a publication about this listed here, so if you're interested, you can find more information there. just zoom in at the Paris region to see how this surface NO2 product already provides a very nice results, very fine details of 1 by 1 kilometer resolution, and you see the NO2 signal of all the small communities in France displayed here. Okay, so more about the scaloscope. Well, it just started at the beginning of this year. So what are the plans for further products? So this surface NO2, we want to use the same technique to also go to surface ozone, because ozone is a very important product both for climate studies and local air quality. Can be very well damaging to the local environment and plants and human health. And after that, we're thinking, or we're actually already in the process of developing a 3D NO2 version. So the current surface NO2 product will be extended from not providing not only surface NO2, but also NO2 levels at some discrete higher levels up to 5 kilometer altitude. This is, for example, interesting if you also want to look at transport of NO2. And then there is another NO2 product where that is fully based on observations in situ and tropomi satellite data, so without any auxiliary data sets. There you sacrifice a bit the time resolution. It gives more monthly and seasonal NO2 products, but at least you have the guarantee that's purely observation based. And that's an algorithm that's also already published, and there's a website mentioned here where you can have a further look. Then
Thank you very much. Unfortunately, we are out of time.
Okay,
already.
Sorry for that. I can actually show the conclusions.
Please show the conclusions quickly.
Yeah. Okay, so actually, so these products will be implemented over the first 2 years, and I'm hoping to hear your feedbacks. Just drop me a quick email if you think that this can be interesting, or if you think that some products could be interesting but are still missing in the system. Thank you.
Thank you very much, Sharon. Next, we will go to the next session, which starts immediately after this one, so no break in between. I also thank everybody for the presentations, and this is the end of my role here as a chair. So I think it's Eleni, you are presenting the next chair and the next session.
Thank you, Nico. Thank you very much, and thank you to all the presenters. So the next session is on aerosol in situ measurement techniques, and it will be chaired by Professor Jean Siard. So, Jean?
Yes. Hello again from my side. We have a total of 7 talks now before the next coffee break. The first by Uwe Florian, Nanodust, Germany, if you are with us.
Yes, I'm here. Let me just quickly share my screen. Okay, can you see my screen?
Yes, all good.
Okay.
Go ahead. You have 7 minutes. Thank you.
Okay, thank you very much. So yeah, today I'm going to talk a little bit about our EU-funded MeTrap project that we are involved in with Nanodust. It is a big project. The data that I'm going to present today is from our side and also from Meta. So Meta's also contributed to that. But the whole project is, as I said, quite a large project that is related to mitigating transport-related air pollution. So we're really looking at the air pollution, how it's created at the source due to transport. There is a lot of project partners involved, so I will not talk about the complete project. You can imagine it's quite a complex project. It's run by the National Center for Scientific Research, Democritus. They are the organizer of the whole thing. And the objective of the project is to create new measurement technologies to actually measure the emission or the air pollution at the emission sites. It's focused on transport-related air quality parameters coming from traffic, from ports, from airports, and railway stations. We plan to create really a more dense monitoring network of up to 30 monitoring stations in 10 different European cities. So we really need to create new technologies to actually monitor the air pollution right at the emission sites. And that's where we with Nanodust are involved in the project. Our part of this is actually to improve the ultrafine particle monitoring. So when we talk about ultrafine particles, I guess most of the community here knows, we are talking about particles that are smaller than 100 nanometers. So it's an additional air pollutant in addition to PM2.5. That's now also on the list of the WHO, and that has also been included in the new European Air Quality Directive to be monitored by the member states. It's usually something that's created by men. It's something that comes from combustion processes, from brake emissions, from biomass, but also indoors. There's work processes like 3D printing that can create these ultrafine particles. And our idea is like, well, how can we create a more dense monitoring network to really monitor the ultrafine particle pollution, not only at high-end stations somewhere, but really at the sources where they are created. And me personally, I was involved very much in the industrialization of ultrafine particle measurement technology. So I worked for HORIBA before, but I was also involved a little bit in transferring, let's say, more scientific measurement technologies to something that is now applied for legal measurements in the automotive industry. And if you look at the history, everything started from, let's say, scientific developments as usual, and then these get commercialized. And then you have these CBC technologies and SMPS technologies that can actually measure very accurately and give you very much information about your aerosols and the ultrafine particles. But then everything moved to actually legal applications in the automotive industry. So cars, you have to get for your type approval, you have to measure them quite a lot in terms of ultrafine particle emissions. And then once this car is in operation, there have now even been regular measurements in workshops introduced that these cars need to be checked in the workshop. And you see the number of instruments that are used in the field increases quite a lot. So we now have about 40,000 instruments in the field. And with more instruments, the prices drop. So that gives us an incentive that we can actually create a more dense monitoring network. So the question is, can we use these instruments that we use for emission measurements in the workshops that are used by, let's say, not very high-skilled personnel, but that can make legal measurements? Can we use them to do more like this ambient air quality monitoring? There's a few differences in the requirements in terms of what particle sizes need to be detected and what concentrations need to be detected, and also what type of particles need to be detected. So our ambition here was to actually take these PNPDI instruments and make an ambient monitor out of it. And this is the solution that we got. So our AirPN10 is now finally developed and commercially available. We developed it within this MeTrap project. We took a PNPDI instrument from these workshop measurements as a basis. So we have the full supply chain that's behind that, also the quality control and the traceability, how these instruments are built. And we optimized it down to particle sizes 10 nanometer to be measured in alignment with the European Air Quality Directive. And we also improved the concentration to a lower concentration a little bit. It's designed really as a standalone instrument that you can just plug and play, put somewhere outside. So it's waterproof. It directly transmits the data into the cloud. It has a lot of self-checks involved. But the way it works is compared to these CBCs, we are using a diffusion charging technology. So the way we are detecting our particles is we charge them and then we give them to a very sensitive electrometer. And this electrometer, depending on the number of charges it detects, it will tell us how many ultrafine nanoparticles are in there. So we get a concentration, but since we have a two-stage detector, we also get an idea of what the average GMD, the average particle size of the particles is. Now, this instrument comes from automotive industry, and the automotive industry only measures solid particles. Now, the ambient monitoring people, they're rather interested in the total particle number, so they want to have all the particles, not only volatile particles, but also particles, not only solid particles, but also particles that are less thermally stable. So usually in a emission measurement, you would actually exclude all of these volatile particles, so you would run them through a volatile particle remover. We implemented an aerosol switch that I can actually switch going through that part or bypassing it, so that we can actually optionally remove or not remove these volatile particles. So we get, in the end, 4 quantities that we measure. We measure the particle concentration of the solid particle number and the total particle number and the respective diameters. On top, we implement also a sampling system that you really can just put it outside and don't have any problem with humidity or any PM 2.5 particles that might interfere with your measurement signal. So how well does it work? This is like one of the first measurements that we did before we jumped into the project to actually see whether it works. And this compares one of the measurements against the reference CBC. And you can see that even below levels that the WHO anticipates of something that might be a limit value, we can actually follow the trace of a, let's say, more accurate CBC quite well over time. But that's not enough. Of course, we needed to metrologically verify everything, and our project partners at Metas, they did a full type approval of the instruments, so similar to what would be done with one of these PNPDI measurement instruments. They did a full evaluation, and they verified that we can actually go down to these low concentrations that we would need for air quality measurements. So we lowered the concentration range for which the instruments work to something like in the order of 1,000 particles per cubic centimeter. And it works under different ambient conditions. So it's really something that you can just take, plug and play, and put somewhere and start monitoring ultrafine particles. We also, of course, did some first applications. This is something from our back office where you can really see the benefit of the instrument. You see that every time, for example, at 6 p.m., we saw a huge increase here in the ultrafine particle pollution. And we thought, okay, what's the root cause of this? And we found that there was quite a clear correlation to where the wind was coming from. So every time where the wind came from this residential area around our office, we saw this huge increase at night. If it wasn't coming from the other direction, we did not see it. And from there, we can actually see that this is coming from this oil-based heating in the residential area. And we can not only see it from the time when this happens and from the wind data, but also from the diameter. So we saw every time that this is happening, the solid and the total, the particle size of the solid and the total particles is roughly the same. If this emission is not there, then they start to deviate from each other. So this red curves, what you see is the geometric mean diameter of the particles. The lighter one is the solid ones, and the darker one is the total ones. So there's some deviation here. You actually see that on average they are quite similar. We also saw some other events because we are located in, let's say, an area where there's also other business activities. So we are close to a slaughterhouse and somebody who's smoking fish all the time. So when that happens, we can also see additional emissions there that's not coming from the residential heating. And then we can also see different characteristics of the particle sizes, but also on the relative concentrations of the total in the solid particle number. So it gives you an indication, not only like what is the actual pollution, but also where does it come from. We will check out our website end of June. So we will host our cloud dashboard from our monitor that we have outside of our building. And you can see what kind of data is available from the instrument. And just if you're interested in it, you can also download it. So what's next? The next step in this METRAP project is that we take these instruments that we metrologically verified in an application, and we will take them to 10 different cities in Europe. The campaigns just started where we built these cost-effective air quality monitoring boxes that we put right next to emission sites. I think in Athens and Lisbon, first campaigns just started. Rotterdam is going to be the next. And then we're going to move these boxes through all these 10 cities. And then we're going to see how the emissions actually are near airports, near ports, near traffic junctions and things like that. So it's going to be very interesting to see how high-resolution stations that are put somewhere in a city compared to actual ultrafine particle pollution close to an emission hotspot. And that's what the European Air Quality Directive is all about. Understand the background, but also understand what are your hotspots, and then we need to mitigate. We need to find solutions for improving the air quality there. And that's all I wanted to present today. Thank you very much for your attention. If you have any questions, project.
Thank you very much, Florian, for your presentation. If you can answer just in a few seconds, a short question from Patrick Weber. If you can please estimate the lifetime of the filter, which is the last step at the electrometer before it changes its airflow behavior, the delta P.
Yeah. So we are not only, I think that's the main advantage that we have, is that we not only provide a sensor, but we provide a complete instrument. So we have a, let's say, complete dilution system with pumps, mass flow meters, and everything. So it's a very controlled environment. So far, we haven't seen, so we simulated this for about a year, and so far we haven't seen any change that would change the characteristics of the sensor in terms of the pumps. Of course, it will depend a little bit on your pollution. I'll need to be honest, yeah. So it's not like I can judge for every site at this point. So it's just we just finalized the development, but we think it's probably around a year that this will last. So after a year, you need a maintenance and the calibration.
Thank you, Florian, again for your presentation. We have to move to the next one. Thank you again. So you have another question in the chat, by the way. So if you would like to answer, I remind the people attending this workshop, if you have questions, don't raise your hand. Just put your questions in the chat, and the presenters will answer in the chat as well. Moving to the next presentation from Matic. Matic, I see you here. I see your presentation. Everything is ready. You can just go.
Okay, so let's check if you also can hear me.
All good, all good.
Okay, so thank you very much. Good morning to everyone. I would like to welcome you to my presentation. My name is Matic Ivancic. I'm a researcher at Rosol McGee Scientific. So today I'm going to talk about new telemeter model, AE36S, the instrument used for measuring black carbon. So the new model has 2 additional wavelengths, allowing us to improve the source apportionment. So telemeters are filter photometers that are most frequently used to measure black carbon. There are 3 models. AE33 is approximately 10 years old and widely used globally, and it's still available. So AE36 and AE36S are his younger brothers, released last year and contain technical improvements. AE36X, where S stands for scientific version, also has 2 additional wavelengths in the UV region. So traditionally, wavelength-dependent measurements of optical absorption can be used to apportion black carbon between 2 sources: fossil fuel BC related to traffic emissions and biomass burning related BC. So plotting the diurnal profiles of both components shows that their typical diurnal profiles are quite different. We can see 2 peaks of traffic-related BC for both rush hours here with gray, and a high nighttime concentration of biomass burning-related BC with brown. So as mentioned, the main topic today will be the new telemeter, and the main question is, can shorter wavelengths of the new telemeter provide more information about the sources and age of aerosols? So we added 2 new wavelengths, 340 and 400, to the existing 7. The wavelength 400 was chosen to stabilize the estimation of the absorption angstrom exponent, and 340 nanometer wavelength was selected to better characterize the optical properties in UV. We also found that using 2 absorption angstrom exponents instead of 1 can better describe the wavelength dependence of optical absorption. So here we have 1 angstrom exponent for longer wavelengths between 590 and 950, marked with green color on this graph, and another one, an orange color, for shorter wavelengths between 400 and 590. So if we extrapolate the line with angstrom exponent, we can observe that the measurement at 340 are consistently below the theoretical exponential curve, and also the measurement at 370 are usually slightly below this line. So, and this is actually the relative difference between the expected and measured absorption at 340 nanometers, marked with blue. And we believe that it can be used as additional information for a source apportionment. Now we can transform this information into 3-dimensional space. So the angstrom exponent for longer range wavelengths on x-axis, angstrom exponent for short range wavelengths on y-axis, and the relative difference on z-axis. But first, we prepared a manual classification for well-defined episodes on 2D angstrom space. So these are results from our site in Ljubljana. Here is the angstrom exponent for longer wavelengths, and here is the angstrom exponent for shorter wavelengths. So low values of both angstrom exponent are typical for traffic-related black carbon. On the bottom of this space, nighttime aerosols with brown carbon have higher both angstrom exponent here, and aerosols related to Saharan dust events are on the upper left part on the graph. So short wavelength angstrom exponent is much higher than the long wave range. We also observe similar pattern for other sites. So here are the data sets from Ljubljana on the top left, data set from Barcelona, and data set from Athens on the bottom left, and data set from Velenje in Slovenia. So by putting all the information together on a common graph, we could confirm that the pattern is repeated for all sites. And yeah, that was some manual classification for some chosen periods for also well-defined fingerprints. And in next step, we try to classify all situations, not only the manual picked ones. To do this, we used a clustering method from the scikit-learn Python library for unsupervised classification. And these are results of automatic clustering from our campaign in Athens. We found that 7 is the optimal number of clusters for this data set. So let's check each cluster into more details. These are our results from the first cluster. On the left, there are 3 slices from this 3D space. So here is 2D angstrom exponent of both ranges on the upper left. Here is the angstrom exponent for short wavelengths and the relative difference. And on the bottom is angstrom exponent for longer wavelengths, and again, the relative difference at 340. On the right side here, we have a typical diurnal appearance of these aerosols. So we could clearly see morning rush hour peak here. So the first cluster consists of fresh aerosols related to traffic. Second cluster can be observed during nights. Both angstrom exponents have higher values, so we assume these are brown carbon related aerosols. The third and fourth clusters, so with blue and orange, have a typical afternoon diurnal profile, so we expect them to present aged aerosols. We assume the third cluster contains aged aerosols with a transparent coating, and the fourth cluster contains brown coating. So for the moment, this is still an assumption, but we are working on a publication there. So yeah, in 2D angstrom space, here we could see that aerosols from the first marked with gray and the third cluster marked with blue are located in the same subspace, but the relative difference that can be seen here or here is different for these types of aerosols, and also the diurnal profile of blue and gray is different. So we assume that there are different types of aerosols. The fifth cluster is placed on the bottom left of the 2D angstrom space. So based on laboratory experiments, we assume that this is a fingerprint of larger aerosols, and last 2 clusters belong to special events, red for wildfire, plum, and yellow for Saharan dust event. So for Saharan dust event, the difference between the 2 angstrom exponents is the most significant. The absorption angstrom exponent for longer wavelengths is low, approximately around 1. And in contrast, the angstrom exponent for short wavelengths is much higher, 2.5 in our case. And this is the fingerprint of the wildfire plume between August 12 and 15 last year. So what is also interesting is that we can observe the difference between fresh and aged wildfire plumes. So both phases of wildfire are placed in the same subspace in 2D angstrom space, but the relative difference at 340 is quite different, and between fresh and aged aerosols. So let's summarize the presentation. I showed the new telemeter model AE36S, which has 2 additional wavelengths compared to its older brother AE33. We presented the use of this additional information, so it's possible to extend the source apportionment to more than 2 components. In the Antonian case, we were able to cluster aerosols into 7 groups with different optical properties and different diurnal patterns. And yeah, if you want to learn more about the topic, I would like to invite you to our presentations at the upcoming AAC conference at the end of the summer. So thank you for your attention.
Thank you very much, Matic, for your presentation. I don't see any questions, but if you have any questions, please feel free to put in the chat for Matic. I would like to move to the next presentation and invite Andrea Baccarini. If you are, yes, I can see you here. If you can share your presentation.
Okay, do you see the presentation?
Yes, if you can put it in full screen mode.
Should be full screen now.
All good, all good. Yeah, go ahead.
Okay, okay, perfect. So hello everybody, I'm Andrea from Aerospec, where we have developed the world's first automated FTIR instrument for PM chemical analysis. I know that maybe not many people are familiar with FTIR for particulate matter measurement. So I just want to do a very short introduction on why FTIR is a very good technique for PM composition measurement. So essentially it's very rapid and non-destructive. Most of the PM2.5 constituents are represented in the infrared spectrum, and in general, the absorption intensity is directly related to the bond abundance. So this really forms a good basis for quantitative analysis. And the previous studies have shown that there is very strong mass recovery, higher than 95% for functional group. Furthermore, FTIR is used routinely on filters in monitoring network, especially in the US. So there is an extensive data set with more than 200,000 samples that is available. And however, filter analysis is typically slow and laborious, not easily scalable, and as you probably are familiar with, affected by different types of interference and sampling artifacts. I just want to show one results from a study based on filters where we can just see that essentially just based on FTIR, we can recover most of the PM components as I just mentioned. So all the carbon-related variables, organic carbon, elemental carbon, total carbon, and BC, but also metals. So for example, silicon, aluminum, calcium, titanium, inorganic salts, so sulfate and nitrate, and overall very good closure also on the PM2.5 mass. So the technique is very promising, but so far it has always been limited to filter analysis. So yeah, as I said, slow and affected by artifacts. What we did at Aerospec was to develop the air monitor, which essentially enables a near real-time measurement with FTIR. So here I have a very simple sketch of the working principle of the instrument. We use a cyclone. This is typically operated at PM2.5, but can be adjusted so we don't have a strong limitation on the size that we collect in the instrument. We have a unipolar charger to charge the particles, and then a collector, which is really the core technology of our instrument that was developed by Nikun Sudani, the CEO of the company, during his PhD. And this essentially allows to have a uniform collection across all particle sizes. We collect these particles on an infrared transparent window. Then we have internal automation inside the instrument that essentially move this window to an FTIR spectrometer to measure the absorbance. Then we use cleaning. Currently, we're using CO2 snow jet cleaning, but we're also exploring other technique to clean this window. Then we measure the clean crystal, and then we start again with the collection. So essentially, we don't have to change filters, for example, but they're always reusing the same crystal to continuously measure on the same substrate. And this allows us to achieve typical collection times down to half an hour, roughly. But of course, this is typically adapted or adjusted based on the ambient concentration. So if it's more polluted, like concentration higher, we can use shorter collection times. Otherwise, we can go longer to increase the signal to noise ratio. I think one of the key features of our instrument is that there are no vacuum parts or sensitive electronic components. Also, the FTIR spectrometer is very robust. So this is really a good instrument for long-term field deployments, and is not very sensitive to ambient conditions. Limit of detection at 1 hour sampling are typically in the 0.1, 0.2 microgram per cubic meter range. So good for most ambient application and conditions. And I just want to show this is a scanning electron microscopy image of ammonium sulfate particles collected on this IR transparent window. So as you can see, we have essentially very spaced particles on the crystal on this window. Data analysis, we use AirSpec, which has been developed by Satoshi Takahama, also a co-founder of the company. And this is open source, so everything is very transparent. There is no black box algorithm in the way the data are treated. And for the quantification, essentially, we just use reference absorption coefficients from literature or NIST or previous calibration. The standard sampling parameters like flow rate, sampling time, and similars. And then two parameters that we control and we measure that are essentially the charger transmission efficiency and the deposition area. So there is no additional correction factor. And this, again, is a very good indication about like the ability of using FTIR for quantitative analysis of PM chemical composition. So I'm now showing also some data. This is quite interesting also from the National Observatory of Athens. So we were just there a couple of months ago, March and April this year. And this is essentially a time series from a full month of measurement. So you can see the bar plot with the major inorganic components of sulfate, nitrate, and ammonium, and the organic functional groups. And in red, you see the reference PM2.5 mass. So as you can see,
Andrea, I'm sorry, I'm not sure we're seeing your presentation. I see you, but I don't see the presentation. No, it's okay, it's good, sorry.
Okay, do you see the figure?
No, all good, sorry.
Okay. So you can see that there is a very good agreement with the reference PM2.5 measurement. And essentially, we are really able to give the full speciation of organics and inorganic components. And again, I would like to reiterate that all the calibration factor, like there is no specific calibration factor applied to this data. It's really just the reference absorption coefficient, which again, I think is quite impressive. And this is essentially just the total PM2.5 mass with reference on the x-axis, and on the y-axis we have the concentration estimated from the ions, essentially just summing up all the contribution from the different components. And here is just a reference, just one spectra from the field, just to show you a bit how these spectra look like. There is also more stuff that we are currently working on, so we can also see mineral dust, and we are implementing this in the analysis right now. So to conclude, the Airmon enables near real-time quantification of organic functional groups and major inorganic PM components. With the data from Athens, we showed excellent mass closure with reference PM2.5, and I think it's important that, I mean, this is real ambient data, so it's not just calibration or lab results. Infrared spectra in general can also be used for source apportionment and provide complementary information to compare to like AMS, ACSM type of approach. Like we're working on that at the moment. We don't have results to show yet, but previous lab studies have shown, for example, the ability to differentiate, like to keep a source signature also after aging. So this is quite promising. And in general, the Airmon is a fully autonomous system, requires minimal user intervention, and so is very well suited for long-term operations. And this is it.
Thank you very much, Andrea. I have a question from Franco regarding the potential use of your instrument in PM10 for, I guess, for mineral dust.
Yes, we can certainly use it for larger particles. The main thing when we have like a significant concentration of larger particles is that scattering becomes quite important. So essentially, we just need to model the absorption in a slightly different way, where we take into account both scattering and absorption, and it's not just total extinction. But this is can be done, and there is already a lot of like reference spectra of all the different minerals. So yeah, this is also something we are working on to really be able to quantify, for example, silica or different aluminum silicates, goethite, and other minerals as well.
Thank you very much. Very interesting presentation. Thank you again, Andrea, for your presentation. I would like to move to the next, provided by Maria Serrato Alvarez. Maria, if you are with us.
Hello. Uy. Sorry. Can you hear me?
Yes,
Okay.
we can hear you, and your presentation, we can see it, not in full mode yet. Yeah, okay, full screen, all good. Go ahead.
Okay.
Thank you.
Thank you. Good morning, everybody. I am Maria Cerrato, a postdoctoral researcher from Physical Chemistry Department at the University of Castilla-La Mancha. I'm going to present our project where we are developing an online instrument to measure oxidative potential of aerosol. The World Health Organization identified particulate matter, for now PM, as a major global health threat. PM exposure is linked to respiratory and cardiovascular diseases due to the generation of reacting oxygen species from now ROS in the body. ROS can be inhaled with PM exogenous or produced internally endogenous through interaction with radioactive PM components. When ROS levels are very high, exceeding the capacity of the cellular antioxidant system, produce oxidative stress. This internal ROS production defines the OP, which is now used a new indicator in the European Air Quality Directive. The most common way to measure the OP is the cell-free assay method. The process usually involves mixed chemical markers like ascorbic acid or DTT with PM sample and monitoring the rate at which they are consumed. This consumption rate is identified of ROS generated. The depletion of this is measured by spectrophotometry. In this work, we have used ascorbic acid assay. This method is simple and accurate. However, traditional applications take a long analysis time and needs bunch of lab equipment, which make it hard to use in portable systems. Therefore, more portable real-time monitoring solutions are now being developed to overcome this limitation. In this context, an electrochemical sensor using a screen printed electrode modified with nanomaterial was developed to monitor OP. The method measures ascorbic acid consumption after its oxidation by PM using a direct electrochemical technique. In addition, studies have been carried out to achieve semi-automation of the detection system for future integration into an online instrument. In this work, we have used commercially available screen printed electrodes as sensors. To improve the sensitivity and selectivity of electrode, a 3-step modification protocol was applied. First, electrochemical activation using hydrogen peroxide. Second, electropolymerization of a conductive polymer. And finally, electro generation of platinum nanoparticles. As we can see in the figure, after electron modification, the oxidation potential of ascorbic acid shifted by approximately 600 millivolts, improving the selectivity. Two configurations were used for the electrochemical measurement. Both use a commercial flow cell. To optimize the method, flow injection analysis was used. In this configuration, the sample is injected into a continuous flow carrier stream. The reaction of ascorbic acid with the particle component happens externally. When the samples are ingested, a narrow sharp peak appears, whose height is related to the ascorbic acid concentration. Applying different injections at different reaction times, we can obtain the rate of ascorbic acid loss. To automate the process, a second configuration was designed. In this case, the sample is mixed in a reaction chamber and then passes through the detector for a period of time, allowing real-time monitoring of ascorbic acid consumption rate. In this case, in tests of having points at different times, Here we have a continuous line whose slope corresponds to the ascorbic acid consumption rate. Several experimental factors that could influence the assay were evaluated, including buffer purification by resin, sonication of the solution, and temperature variation. Observe that the blank signal when particle sample is not added decreased significantly when using resin. Buffer sonification didn't produce significant improvement. The reaction temperature presents a very significant effect on the test response. All these experiments were performed in parallel with the classical method, obtaining a good agreement. To fully understand the effects of the concentration of radioactive compound PM, OP was measured for quinone, iron, and copper at several concentrations. As we can see in this figure, the response curves increased linearly with the concentration for iron and quinone, but not for copper. Among the analyzed, copper exhibited the high slope, including only the linear range, indicating the highest reactivity, while iron saw the lowest. All these experiments were performed in parallel with the classical method, obtaining excellent agreement. Finally, preliminary studies have been made to achieve semi-automation of the detection system. In this figure, we can see the time signal of ascorbic acid obtained for sample with copper and blanks. An increase in electrical current indicates the initiation of reaction kinetics. The signal will decrease due to the reaction. The slope of the current time curve was found to be dependent on the rate of ascorbic acid consumption, making it a valuable analytical signal for quantitative analysis. As shown in the figure, the results are consistent with the data obtained using the flow injection analysis and the classical method. In summary, we can say that a novel electrochemical sensor has been developed for the monitorization of OP based on ascorbic acid assay in PM. Key parameters influencing sensor performance were optimized. The flow injection analysis system demonstrated excellent analytical performance to model oxidants and strong agreement with the classical method. The results are highly promising for integrating the electrochemical cell with an online aerosol collection system, enabling the creation of a full autonomous instrument. And finally, I would like to thank the funding entities, the people involved in the development of this work. Above all, thank you for your attention.
Thank you very much, Maria, for your presentation. I don't see in the chat any questions, but you still have some time to think of questions. And Maria, check the chat to see if there are some questions popping up later on. Thank you again for your presentation.
Thank you.
I would like to move to the next one from Patrick Weber. Patrick?
Yep.
You are with us? Yes.
Still here. So, where is it? Okay. Wonderful.
Yeah,
okay.
Good. Go ahead.
Wonderful. Hi, greetings from the Research Center Jülich. I'd like to present you what we are doing here at the Jagos Aerosol Lab at Jülich. And with we, I mean Oliver Bischoff, Sarah Kirchhoff, Andreas Petzold, Ulrich Bundke, and of course me. So first, I think you all probably know, but nevertheless, first, a condensation particle counter. What does it do? So it's for total number concentrations for aerosols, purely counting, and even for very small particles, and it uses a working fluid by vaporizing it and then condense them onto these particles, making them grow in size, and then we are able to detect them optically with a laser or something like that. So first, working fluids can also cause problems, especially if you want to bring them onto an airplane. I mean, alcohols like butanol, extremely smelly and flammable, may cause issues. And if you use water, you can maybe have difficulties with mold, with algae grow, and a very high consumption, and for scientists, a very high seed dependency. So we had a look on on a search for a new working fluid, and we found one in a DMS cycle. So DMS, dimethyl sulfide, is emitted by algae in the range of several teragrams per year, and then the end step it's sulfate. And as an intermediate step, there's DMSO, dimethyl sulfoxide. So it's an organic product, and there's no accumulation in nature, which is very nice. But how it is in comparison with the other working fluids I mentioned, so it has the advantage as water that it has no hazardous properties, but it also has very low vapor pressure when you compare it to butanol or water. So when we use it in a CPC, so we use it on multiple types of CPC and CRIM CPC and on TSI CPC. And of course, Yagos uses aircraft for measurements. We also were very interested in the low pressure behaviors. So we tested them to 200 hectopascal, which is around 10 kilometers flight height, which passenger aircraft are flying. So and as you can see, the butanol and the DMSO working fluid inside the CPCs behaves the same at each pressure level, which is great, and we already published it, if you want to see it in aerosol research. So, but we have had a deeper look. You can vaporize a fluid and condense them onto an aerosol, but what about a solid material? You can sublimate it, so without going to a liquid, directly to vapor, and then also deposit it onto an aerosol, making them grow in size, and then we are able to detect them. So our very first proof of concept experiment, we used POPs, optical particle spectrometer, as an optic set. We, as you can see at the lower left, we have first the, let's say, it's a typical ambient aerosol, so very low concentration with sizes to a maximum of 200 nanometers. And then when we starting the sublimation process, you can see we reach the same level as the CPC with the number concentration, and the aerosols grew in size to larger than 1 micron. So we have the same process, but without the working fluid. So then we have a closer look on with the prototype to a little bit, so the POPs prototype, we with the cutoff efficiency, you compare as well with the DMSO, so the same procedure. You have an electrometer as a reference instrument, and then look at the cutoff, so where is the 50% counting efficiency, and it's in the range of the butanol CPC. So we are talking about plus minus 1 nanometer, 2 nanometers, but the D90 is very close to it, so the 90% counting efficiency. Well, for comparison, so the DMSO for the consumption is very low. So butanol with around 100 milliliters per day. And when you compare it with the DMSO, the working fluid we found, we have 2 milliliters per day, which is really, really low. And when the solid we found, we are talking about a consumption rate from 1 gram per month. And of course, the solid also has no hazardous properties. That's also nice. Yeah, well, to my summary. So we found DMSO as a promising substitute for butanol. So it's very low consumption, non-hazardous, and it doesn't smell. No odor. So great in the lab, great in every use. And it's suitable for ambient and low pressure measurements and applications. And we presented here also the concept, what we call the sublimation particle counter, the SPC, which also is promising for ambient and low pressure measurements. We did some. And yeah, it's a concept without liquids. So nice to have. Still have some patents pending on this. And with it, any questions?
Thank you very much, Patrick, for your presentation. Glad that we don't smell anymore the butanol, and you increase our lifetime somehow. So thanks again. I don't see any questions in the chat, but if there is, feel free to put. And I propose that we move to keep the time. I propose we move to the next presentation given by Olga Zografou. Olga, if you are with us.
Yes. Can you hear me? Can you hear me?
Yeah, not so. Yeah. Go ahead. Share your screen.
Do you see the full mode?
Yeah, we don't hear you so well. If you can speak a bit loudly so that we can
Is
get...
it better
Yeah,
now?
wonderful.
Okay,
Yeah. All
great.
good.
Thank
Good,
you.
Olga. Go ahead.
Thank you. So I'm Olga Zografou from NCSR Demokritos, and here today I will share some results from a real-time source apportionment study using the AXA setup and SOFI real-time. So generally, in atmospheric science, source apportionment is the procedure followed in order to identify the sources of ambient particulate matter, or sometimes gases, by basically deconstructing the mass spectra of all the species in time into the contribution of its source in time and its specific fingerprint or else factor profile. So the traditional methods of source apportionment commonly rely on offline analysis, which has limitations such as delays in data collection and the analysis, and so they offer limited ability to respond quickly to any pollution events. So online instruments offer high time resolution data, which can enable the source apportionment results of high temporal resolution. And also by using online instrumentation, the diurnal variability of species can be tracked. So the growing need for real-time continuous source apportionment can be achieved by deploying online instrumentation and the respective real-time source apportionment software. So in this study, we propose a combination of instruments that provide a quite complete picture of the PM mass. So we propose the use of an ACSM, which identifies non-refractory organic matter and the inorganic ions sulfate, nitrate, ammonium, and chloride. An exact for elemental composition, and an ethalometer for black carbon concentration. Sorry, I skipped. Yeah. So the first step is to deploy these three instruments online for real-time measurements. And from this step, we get the chemical composition, but not the sources yet. So in the next step, by applying the SOFI real-time software, we can treat its instruments separately in an automated way, real-time, and get the results for the sources of its instrument and the real-time. For example, we can get the sources of organics from the ACSM, the elemental sources from the exact, and split the fractions of black carbon into solid and liquid fuel. And then the software performs a reconstruction of the total sources of PM by integrating the individual sources of its instrument into one combined pie chart. And so this is the final outcome that we get, this integrated pie chart with all the sources that contribute to PM. So the study I described today was conducted at the Demokritos site in Athens, which is a suburban site. It's located at the foothills of Mount Timitos, and it's located around 8 kilometers from the city center. And this was conducted in March 2024, and it was a pilot month to test this real-time application, the AXA setup, that is currently implemented in the EU MITRAP project that conducts measurements at transportation hotspot stations around Europe. So here you can see the profiles obtained that we obtained from offline source apportionment, and we also provide in the real-time software. So on the left you can see the sources of elements from the exact, And in the middle, you can see the organic matter sources from the ACSM. So this consolidated pie chart is the result of real-time source apportionment that includes sources like traffic, for example, which combined the hydrocarbon-related factor from the ACSM, tire and brake wear from the exact, and also the liquid fuel black carbon from the ethalometer. So to validate our results, we checked the ratios between the real-time source apportionment results and the offline base case source apportionment results. So you can see the graph for the ACSM on the left and for the exact on the right. So we see that the real-time model application seems to produce robust results. The ratio is close to 1 for almost all sources. So these lines, the red lines, indicate the 10% deviation, and the black line is the 20% variation from 1. And we observe mainly highest variability of the ratio in low concentrations, and for some factors that have intensity events, like, for example, sea salt from exact. So to conclude, I showed you today a real-time application of source apportionment by deploying online instrumentation with high temporal resolution. A number of sources was identified, including both primary and secondary species. And the setup of instruments, the AXA setup, covered the largest part of PM mass. So in the cons of the application of this model, the user has to select a specific number of sources before running real time, which should make him aware of changes that might be needed in the number of factors. And it also creates issues during events where, again, extra factors might need to be considered. And finally, at this time, secondary species like ammonium and sulfate are currently not included in the source apportionment analysis. So I want to thank you, everyone, for your attention. And if you have any questions.
Thank you very much, Olga. There is 2 questions from Marta, but they are very technical. And I think I would like you to look at them carefully in the chat and
Okay.
provide an answer in the chat, because they are pretty technical.
Of course.
But
Thank you.
yeah, so please look at it. And again, thank you very much for your presentation, Olga.
Thank you very much.
I would like to move to the last presentation by Alexander Gundar Graham. Alexander, are you here?
Yes, I'm here. I'm spinning.
If you can share your screen.
Do you see the screen?
I see your screen, not your present. Yeah, in full mode, please. Wonderful.
Okay, do you hear me?
Yeah, all good. Go ahead.
Okay, very good. Let me activate my laser pointer, which I can't find, but Spotlight must be the same thing. Thank you very much for the chance to speak today on a new technology that we're introducing from TOFWERK. And this is a microwave-induced plasma time-of-flight mass spectrometer, and I'll be talking about it as a tool for real-time quantitative analysis of metals and air. So how are metals typically measured in air? So we just had an example using real-time X-ray fluorescence instrumentation, but the most common way that they're measured in air is with lab-based approaches, where particles are collected on filters and then analyzed by an offline technique like ICP-MS or X-ray fluorescence. However, they could also be analyzed in the field, where particles are collected on a filter and then analyzed, for example, by energy dispersive X-ray fluorescence. These are really bulk measurements because we're collecting an ensemble of particles on a filter, and we're getting pseudo real-time measurements in the order of 30 minutes to 2 hours, something like that, with reasonable detection limits for what we need to measure in terms of metals in the air of sub-nanograms per cubic meter for some elements. So the instrument that we've introduced at TOFERC is this microwave-induced plasma time-of-flight mass spectrometer, and it combines a microwave inductively coupled plasma atmospheric pressure source to a time-of-flight mass spectrometer. What's unique about this plasma source is that it can be operated with nitrogen. Because we operate the source with nitrogen, we can generate the nitrogen in the field, and so we don't need any compressed gases to run the plasma, so this is a field deployable instrument. The plasma is also robust for the introduction of air into the plasma, so we can directly introduce particles into the central channel of the plasma, vaporize those particles, and determine the mass of different metals in those particles. And it's sensitive to detection of metal particles in the attogram to femtogram range. The instrument is rather large. It's field deployable, so it can be put in a vehicle or on a site. It consumes a fair amount of power, 5.5 kilowatts, but it runs simply on power because we're generating our gas on site. This is a video of the microwave plasma pulled back away from the interface of the mass spectrometer, not how we would typically run it. But I just wanted to give you an idea. This is a very hot plasma, so it's around 5,000 Kelvin. And when we introduce particles into the central channel of this plasma, they're completely vaporized, atomized, and mostly ionized. And then we extract those ions into the mass spectrometer. We introduce ambient aerosols into the plasma using a pneumatic nebulizer as a Venturi pump. So we introduce around 100 to 250 milliliters per minute of air directly into the plasma. And then, of course, the metal ions that are generated in the plasma are transferred to the time-of-flight mass spectrometer. This is what it looks like in a schematic diagram. In a real life setup, it looks like this, where we have our sampling pneumatic nebulizer pump. And if we hook this up to the instrument, we can directly introduce air into the plasma and get trace metal concentrations of metals in the air. We can analyze most metals by the MIPTOF. And if we look at the sensitivities that we're able to achieve in counts per femtogram, they look like this. So for the most sensitive elements, we're in sort of the 50 counts per femtogram. If we then look at detection limits in terms of nanogram per cubic meter, you can see that for most of the elements in a 1 second analysis time, we're in the sub-nanogram per cubic meter detection limit, with some other elements for which we're less sensitive in the tens of nanograms per cubic meter in terms of the detection limit. We've done some initial field campaigns to prove the fieldability and application of this instrument. So we did one with PSI, and we also did one with Aerodyne. And I just wanted to give you some example data from the kind of measurements that we can make. So here, for example, is collaboration with PSI, where we're positioned next to a train track here in Thun, Switzerland. And we can see that when the train when a particular outbound train passed us, we could see increased concentrations here of copper, iron, manganese, and copper. So we can look chromium. So we can look at the plume, and this plume has specific copper, iron, and chromium compositions. This is at the single particle level, so we can see the elemental composition at the single particle level, which could be attributed to a source. Another example is when we're driving through Boston with the Aerodyne mobile lab, and here I have plotted the different elements that we're measuring as a function of time. And you can see two clear events where we had very high concentrations of metals. And these occurred when we were driving through a tunnel in the Boston area. And if we take one of these events, which we're measuring at, we're averaged here at 10 seconds, and we rather look at very high time resolution data, we can actually look at the single particle measurement in one of these events. So for example, here's the correlation of hafnium and zirconium. These are geochemical twins, so they have a very good correlation. On the other hand, if we look at the correlation of barium, tin, and antimony, three elements which are indicative of brake wear versus iron, you can see that the correlation is there, but not as conserved. And this is likely due to different models of brakes and cars, et cetera, that are producing the brake dust in the tunnel. Finally, one other example, we had the Aerodyne Mobile Lab, and we positioned it around 200 meters downwind of a runway. And here you can see for light aircraft, single propeller aircraft, the plumes of lead that are emitted when the aircraft take off and land. This is because general aviation fuel is still leaded. So we can see these plumes of lead in real time at second resolution or even lower. So with that, I'd like to conclude with the MIPTOF. We have real-time measurements of trace elements in air. We can do bulk measurements in terms of nanograms per cubic meter, but also particle resolved analysis. And applications include things like source apportionment and air quality monitoring for metal-containing particles, such as from brake wear, tire wear, urban dust, mineral dust, etc. With that, I'd like to thank you for your attention and happy to answer any questions.
Thank you very much, Alex. Impressive talk. You have questions from Franco. If it's suitable for transported mineral dust particles, which are metal oxides.
Yes, so the plasma will completely vaporize metal oxide particles up to a certain threshold. We don't exactly know what that threshold is, but it's probably something in the 5 to 10 micron regime. So anything above 10 microns will probably not be completely vaporized in the plasma, and this means it won't be quantitative anymore for the trace elements in it. But anything less than, say, 10 microns, so PM10, PM2.5, we should be able to completely vaporize these mineral dust aerosols.
Okay, great. Thank you again, Alex, for this very nice talk. So we are concluding here this session on aerosol in situ measurement techniques. I would like to thank all presenters for their timely, interesting presentations. We are good on time. You are allowed to take 3 more minutes for your coffee. I would like to give you the floor, Eleni, for the next steps. Thank you.
Great. Thank you, Jean, and thank you again to all the presenters and the chair. So we're going to have a coffee break now. We should be back at 12:15 Central European Time, 1:15 Eastern European Time for the last session and the VPCO sessions. Hello again, everyone. Hi, Franco. So we're moving on to our next session, which is on aerosol and cloud optical properties, which will be chaired by Dr. Franco Marenco, who is an associate professor here at the Cyprus Institute. Franco, the floor is yours.
Hello, everyone. Welcome to this session on aerosol and cloud properties. Actually, we have 5 presentations. If I'm not wrong, they all are on remote sensing techniques. And yes, so I will give, first of all, the floor to Guido Di Don Francesco from ANA Systems from Italy, who is also a great friend of mine, and we used to work together once upon a time. And he's going to give a presentation on LAST, a cutting-edge system for multispectral LiDAR signal simulation. So, Guido, please go ahead.
Thank you, Franco. Let me do. One moment, just one moment. Okay, see? Can you see my presentation?
I can see your presentation, yes.
Okay. Let me try to do full screen presentation. Okay. Hello to everybody. I here is to present a new instrument, the ALA, Advanced Light Application.
Guido, now I don't see your presentation anymore.
No, okay. Let me try. Did the test just a second ago. Let me try. No. Just a second. Okay. What happened? You see?
Now I can see it, yes. It's not in full screen, but you can go ahead like this, yes.
Okay, perfect. So, I am here for ALA, Advanced Light Applications. It's a spin-off of CNR and the University Federico II of Naples. And we will present a new instruments for simulation LiDAR signals, multispectral simulation, optical simulation, to test the linearity of the system, the crosstalk between Raman and main channels, and also to check the crosstalk between polarization channels. That is one of the major issue of the LiDAR system when they have very high powerful emission and so on. So just a quick review for who doesn't know ALA. ALA is a spin-off. We are operative in Naples. We are located in the CESMA Center. It's a facility of the University Federico II. And we are devoted to develop LiDAR systems, ground-based airborne scanning LiDARs, and also we are involved in several space-borne micro LiDARs. And also we develop electronics instrumentation, mainly indicated for the LiDAR, analog and digital acquisitions, and for controlling the laser and all the systems. LAST means LiDAR synthetic optical echo transmitter, is instruments designed to simulate the behavior of the atmospheric echoes, and more have also other echoes simulated like stairs or step to check linearity of the acquisitions of the sensors and so on. So what allows the testing? LAST allows analog and photon counting acquisition compared with one to the other one, so you can check the linearity of the systems. Thanks to the fact that we can adjust the optical power of the emission to several levels, so you can go from very faint photon counting rate to completely analog rates. So you can check with the same signal all the behavior of the photon rate you can check, you can have with your acquisition systems. You can have also the possibility to check the response of each sensor at different wavelengths and different power, optical power regimes. And also you can add independently a background skylight to the eagles, so you can have a change of linearity of the sensors when you have a stronger background from the skylight or you are during the night time. Also, you can check the intensity of crosstalk between channels because we have channels emission in several wavelengths with very small bandwidth. And also, you can have also the polarization of the signals, so you can have also the check of the crosstalk between polarized channels. And also, you can have in the so you know environmental disturbance of. So the main components are three: transmitting dome with LEDs and light lenses, filters, and so on. That should be positioned on top of the LiDAR of the telescope window. Then you have a standalone console with batteries or supplied by the usual lines, and you have a touch screen or the possibility on the right side. You see the possibility to check all the system that you are doing to test by software. You have the capability to install inside the console different curves and to send to the transmitting dome. And also you have in wizard mode several tests in automatic mode. So when you need to for a long time, you leave it on and it works in the test by itself. And a couple of this is you check
Guido, apologies for interrupting, but we can hear very bad. Can you try to switch off your camera maybe to have a better bandwidth, or speak closer to the microphone?
Okay. Let me go closer to the microphone. Okay. Better. So let me. Now is better.
So and so.
Now you see it again?
Yeah, I can see it, yes.
Okay, okay, I speak. So you see the wavelengths on the left side, and on the right side you see the curves that you can upload on the system and you can send to the DOM for deletion. And this is a review of some of the curves you can send, stairs, molecular, and aerosol, for example, to simulate the aerosol and the clouds echoes. These are the channels, optical channels that you are available on the last system, are narrowband signal for polarizing channels. They are on UV and the green, and the outband emission is very small, it's -7, and the crosstalk on the polarization is as well very low, between 600 and 900 parts. So you have also wideband signal for the Raman channels. So the usually Raman channels of the neodymium LiDAR, 8, 6, and so on. And you have also a very high power signal at the 3 band of the neodymium YAG, because usually some systems have a very powerful laser, so you can use this channel to check the sensor linearity and so on. And you have also, as I said, independent skylight background. And you have also optical attenuators that physically you put on front of the lenses to simulate lower and lower rates. And for an example of the use of this system, we have in Chesma the EMPO LiDAR. So we our board's analog and digital counting acquisition, and we checked, for example, the linearity of the analog converter. And on the right, you see, for example, the several levels of power, and you see that in all cases they are don't count and mainly use so don't rate the blue, that is the balloon counting car reading from analog channel, and so you check how is the how is the type rate that you need your balloon counting channels to believe. So it looks the system to test how is the performance of your LiDAR systems, mainly for the YAG lasers. Thank you.
Thank you very much, Guido. Very interesting presentation. I see no questions in the chat, but also I think, Eleni, can you confirm, do we have time for any questions?
No, unfortunately, we're right on time for the next presentation, so we can move
Okay,
on.
so then the next speaker is Alkistis Papeta, who has a very catchy title for her presentation. Can UAV-based and LiDAR synergistic observation improve mineral dust quantification? And Alkistis, please, the floor is yours.
Thanks a lot. Let me also share the presentation. I hope you see full screen.
Yes.
Great. So my name is Alkistis Papeta, and today I'm trying to answer a question, as Franco said, which is, can UAV-based and LiDAR synergistic observations improve the mineral dust quantification? So first of all, why dust quantification is important? So as you might know or not, dust is considered as the most abundant natural aerosol, which comes with its own challenges, amongst which is the high temporal and spatial variability. Also, it has variability in the sources that it can be emitted from, the size, shape, and optical characteristics. And we are also limited in the technological tools that we can observe dust, which can be satellite and ground-based LiDARs, airborne observations, and sun photometers. So dust quantification is important for understanding its radiative impact on Earth's climate and on human health. But there are some ways to quantify dust. One of it is the gravimetric quantification, which actually expresses the quantity of dust matter in the atmosphere or at the ground level, since it's normally observed there. And the optical quantification, which is normally extinction or aerosol optical depth, and it shows how what is the aerosol radiative impact on climate. So the gravimetric method, it's actually normally used from air quality assessments, monitoring networks, and aviation, and it's typically measured by ground-based gravimetric sensors or optical particle counters. On the other side, the optical quantification is normally measured by remote sensing instrumentation, so LiDAR, sun photometers, satellite imagers, and is useful for radiative studies and atmospheric models because they use aerosol optical depth for assimilation purposes, for example. But what is then the translation between these two quantifying parameters? For this, we use the volume to extinction parameter, which is there to relate the gravimetric and the optical properties of aerosols. So focusing only on the first part of this equation, we have the volume concentration on the top and then the extinction as the alpha. And a typical methodology to find this volume to extinction parameter is to use sun photometers to input both the volume concentration and the extinction. So this comes with some pros and cons. amongst the pros as the global coverage of networks like IronNet or Skynet, and also that we normally have long data sets from the stations, that we have sun photometers. But on the cons, we should keep in mind that sun photometers normally give us the column average of the measured parameters, and that their retrieval algorithms, specifically for IronNet in this case, are limited to diameter, and this is 30 micrometers for IronNet. So this is a big problem, especially as there is evidence of giant particles from several airborne campaigns that have revealed a significant presence of giant particles, even up to 300 micrometers. These giant particles play a critical role in the aerosol direct and indirect effects, yet the models underestimate their abundance by up to a factor of 4 by just neglecting their presence. So we come up with a new method, and we thought, why not combining the UAV-based observations and then ground-based LiDAR observations to derive this zeta parameter, which is the volume to extinction. So for volume concentration, we use the UAV measured volume size distributions. And for the extinction, we use the extinction profiles measured by a LiDAR. By doing so, we can calculate the zeta parameter in a different way. And we've tested this method in 2 different campaigns. One was in Cabo Verde back in June 2022 as part of a SCOS campaign. And the second campaign was during fall campaign in Cyprus. During both campaigns, we had observations from UAV-based optical particle counters and also ground-based LiDARs. So by combining these 2 methods, we can derive a vertical profile of the volume to extinction parameter, as you can see here, and I'm going to guide you through this complicated plot. So then blue lines represent the observations. So by calculating the UAV and the LiDAR synergistic zeta, and by just looking at the comparison between fall campaign and ASCOS, as a first result is that we see higher zeta during ASCOS, and this is mainly due to the presence of giant particles. A second observation will be that if we had used IronNet for this calculation, which are these dashed black lines on the plots, we would have underestimated zeta, especially in the case of ASCOS. Another conclusion here is that by using simulations from WRF-Chem, which are these magenta lines on the plots, again, in the case of giant particles, we will have get lower zeta, which is the volume to extinction. Sorry for calling it zeta. This is the short. And the last thing is that we did some shape simulations using the MOPSMAP tool in order to understand the shape of the particles we measured. And it seems like during the fall campaign in Cyprus, during dust events, we observed more spherical particles than in the ASCOS case, which at some altitudes we had indications of more irregular particles. So this brings me to my summary. So volume to extinction relates gravimetric and optical quantity of aerosols. And we've seen that conventional methods like IronNet or models neglect giant particles and therefore underestimate this parameter. This novel method we presented today with the synergistic use of UAV-based OPCs and LiDAR can improve the accuracy of the volume to extinction, especially in the case of giant particles. So all these that I presented today and some more analysis on the origin differences for the zeta parameter can be found in an upcoming paper. And I hope I'll find a way to keep you posted once this is published. So thank
you very much, Alkistis. The floor is open for questions. I don't see any in the chat. So in the meantime, I will ask a question, Alkistis. How do you see? We see that there is an observational gap here between the volume and the extinction measurement. how would you think to address this so that we have a better understanding of the global distribution, let's say, of this ratio?
So by gap, you mean spatial gap, that we don't have many campaigns, or do I get correctly?
Yes, we don't. Yes, exactly. We don't have enough observations. We
So
have
one
your
thing,
UAV observations, but then it's not a global
yes.
observation.
So one thing that I already mentioned is that there are several airborne campaigns that were done in the past to prove this presence of giant particles. Of course, if we had collocated LiDAR observations, we can go back to these campaigns and perform again this analysis. Another thing is that we have some Earth explorers up in this space currently. So instead of using conventional methods like the one that I mentioned, we can think of applying this method also to satellite observations.
Okay, thank you very much, Alexis. I can think of some actually airborne campaigns. What you mean, what you suggest. So we have 1 more minute. If anyone wants to ask a question, please post it in the chat now. And if there is no more question, thank you very much, Alkistis. I will give the floor to the next speaker, which is Max Aragon, who is going to discuss the trinocular all-sky imaging network for cloud and solar applications. Max, are you here?
Yeah. Just can you please confirm you see the screen?
Yes, I can see the presentation in full screen.
Okay, perfect. I will start. Thanks, everyone. I'm presenting this project called Trinocular All-Sky Imaging Network for Clouds and Solar Radiation. You see a bunch of logos here, so it's a joint effort among many institutions. Just to name a few, so WeMathics is leading the project. That's a startup that we recently incorporated in Austria, but also we have partner universities like the University of Applied Sciences in Bonn in Germany, Minpari PSL, then other research centers like GIBS and CIRTA in France, and this was funded by FFG in Austria. Just to give you a bit more of context, this is part of a broader project, which is part of my current PhD at the University of Minpari in PSL, which I'm working on sky camera networks for the retrieval of cloud properties, aerosol properties, and also for solar radiation mapping applications. And I'm supervised by Professor Philippe Blanc, Yves-Marie, and Jehia Issa, and we're based in the south of France. And yeah, just to give you a bit of information also, so I've been installing sky cameras for the past 5 years in multiple locations across Europe, including Hungary. I started in my bachelor's, then in Finland as part of my master's, and recently also to installing in CloudNet stations like the one I'm presenting today. So the latest version is this one here at CIRTA in Palaiseau in France. Also, to give you a bit more of context of the sky imaging, so there are several applications, of course, not only for cloud classification and cloud detection, but also for solar estimation. And in the past few years, the amount of publications for solar forecasting has also been increasing for satellite and for sky imagery. And the thing with the existing technologies and sky imaging is that there are, of course, trade-offs. These trade-offs are with respect to the cost and the quality and the robustness and the maintainability and the autonomy and all these characteristics that we could get from different systems. The thing is that if the costs are relatively high, this is a bit challenging because it makes it prohibitively for installing sky camera networks. And this is one of the main reasons why we started this company called WeMathics, when we try to bring down the cost a bit, but also keeping high quality. So then we can deploy low-cost sky camera networks. I'm introducing here this technology that we're using. We call it a Piranovision, which integrates a thermopile pyranometer for global horizontal irradiance measurements and a fisheye sky camera. We're using Raspberry Pi 5, so it's one of the latest microcomputers. So it's already capable of running AI models within the camera. So this is very helpful for our cloud detection and our solar estimation models. And we also have a relatively high resolution, so 12 megapixels. And yeah, you can see here more of the details. We'll also release soon the data set in a publication, so you can learn a bit more. But I will just jump straight to the data. So we're taking images every 30 seconds. So these are synchronized using NTP, and we're collecting global horizontal irradiance every 1 second. So this is particularly useful for topics like cloud enhancement events, which are typically captured in seconds. And yeah, this is one of the reasons why we get this high resolution. This is the 3-camera network that we installed in Paris. So 2 cameras, CIRTA 1 and CIRTA 2, are pretty close to each other, 600 meters. And then we get another one, which is located at the JIPS laboratory, almost 3,000 or 3 kilometers away. So for sure, CIRTA 1 and CIRTA 2 have overlapping fields of view, but then the one at JIPS, there is not fully overlapping, but we can quickly see the clouds when these are moving in the different images. Yeah, so these are the systems that we have installed. So there are several prototypes and several versions that we've built. For instance, the one at JIPS lacks the pyranometer, so there is no radiation measurement there, but fortunately the laboratory has a PV module there, so we are using those PV measurements as part of our data set. And yeah, CIRTA 1 and CIRTA 2 both have the pyranometer and the fisheye lens. We're preparing the release of the data, so we're planning to open source 3 months of synchronized data every 30 seconds. This is also part of another project called Sky ImageNet in collaboration with the European Space Agency and MIT. And this is for releasing a very large data set of sky images collocated with radiation measurements throughout the world for building also a large AI model. So for us, these are a few of the images collected recently. The next steps are to orient the data from north to south to also perform geometric calibration. We're also collecting nighttime imagery for moon calibration. And we are planning to release the high resolution version and a machine learning ready data set, so low resolution. And as I mentioned, the EHI data, the cloud masks, and also one of the advantages is that this CIRTA atmospheric station is also part of CloudNet. So there are a bunch of instruments there that it could be also helpful, like this one, which is a combination of the radar and the LiDAR data. So this CloudNet target classification product that could be used for volumetric studies and validation of cloud heights. And just to finalize, one of the applications that we've been working on is also the synchronization with polar satellites, especially for enhancing the detection of clouds in satellite imagery. So here the sky images also can support on the detection of clouds or to have a ground-based reference for these satellites. So yeah, just to highlight here, like the actual cloud that the sky image is capable of looking at. So the image on the left is a 20 by 20 kilometer domain. So yeah, that's it. That's all from my side. Thank you very much. And yeah, please keep in touch. And yeah, you can just drop me an email here.
Thank you very much, Max, for this very nice presentation. The floor is open for questions. I see nothing in the chat for the moment, but I will have a question. Actually, yes. So you showed in your last slide, you showed how you correlated a specific cloud in the satellite and in the camera. And since you're mentioning a network of 3 cameras in Paris, are you able to do this correlation of the same cloud in the different cameras on the ground as well as the satellite? And also, are you able to do this correlation in an automated way, or does it need to be done by someone who looks at the images?
Yeah, so For instance, this image, the one on the left, the satellite image that's taken by the Sentinel-2 satellites. And this satellite usually has very large scenes, 100 by 100 kilometers. So this one is actually a small kind of cropped scene covering 20 by 20. Given that the cameras that we have are apart from each other like 600 kilometers and then 600 meters and then 3,000 meters, we can actually correlate pretty well the satellite images with the 3 sky cameras that we have. I think it's somewhere like around this. Not sure if you can see my mouse here, but it's somewhere about this area. And we're actually also working now on the automation of this correlation, specifically for the synchronization. So first of all, the synchronization of the data for the acquisition. So when the satellite is passing over the camera, we start taking images a bit faster. So instead of 30 seconds, we take every 10 seconds to try to capture the best possible match with the satellite. But the other thing is also the geometric correction, because with the fisheye distortion, we also have some issues on the edges. So we are now working on correcting this with the geometric calibration using the moon and also the orientation. So it's not yet fully automated, but that's really the goal. Yeah.
Thank you very much, Max. Sorry for the person who asked the question in the chat, but I think we've exhausted the 10 minutes. So I'll move on to the following presenter, which is Konstantinos Chrysostomou, who will discuss the dual field of view depolarization method using the PolyXT Raman LiDAR of CARO, Limassol National Facility, parameterization of aerosol cloud interactions.
Hello,
Konstantinos,
everyone. Can you hear me?
Yes, I can hear you. I can see your presentation. It's not in full screen.
Not in full screen. Okay. Now?
Yes.
Okay. Wait a minute to find to change the presentation mode. Sorry.
I don't understand why you need to change the presentation, but we can see the presentation.
Okay. So hello, everyone. I'm Konstantinos Chrysostomou, a PhD student in atmospheric remote sensing and atmospheric monitoring at Cyprus University of Technology. And I'm a research assistant at the Center of Excellence. And today I'm going to present the PolyXT Raman LiDAR method using the PolyXT LiDAR of CARO National Facility. Cyprus Atmospheric Remote Sensing Observatory, or CARO, is a ground-based station located in Limassol and consists of an aerosol remote sensing and a cloud remote sensing observational platforms. The aerosol remote sensing platform consists of the PolyXT Raman LiDAR, a Doppler LiDAR, and a distormeter. And the cloud remote sensing one consists of a microwave radiometer and a cloud radar. And by synergistically using these two platforms, complete insights into the atmospheric dynamics, the aerosol load in the atmosphere, as well as the dynamics of the clouds, can be offered. So the PolyXT Raman LiDAR, which is the one used in this study, is a multi-wavelength LiDAR system used for detailed atmospheric profiling, and it operates at 355, 532, and 1064 nanometers, capable of measuring also the Raman shifted molecular signals at 387, 407, and 607 nanometers. And it is able to measure 2 different field of views with 8 far-range channels of 1 millirad field of view that you can see in this blue box here, and 5 near-range channels of 2 millirads field of view that you can see in the purple boxes. From this system, the backscattering extinction coefficients can be derived, as well as a volume depolarization ratio at 532 and 355 nanometers. The dual field of view polarization LiDAR technique is a method that was developed by Christopher Jimenez in 2020 as a follow-up development of the dual field of view Raman LiDAR technique. This technique can derive crucial information about the microphysical properties of liquid water clouds, such as the droplet number concentration, the effective radius of the droplets, the liquid water content, and the cloud extinction coefficient. And by using the information of the vertical wind from a Doppler LiDAR and by applying the polyphony method, detailed studies of the impact of aerosol particles on the microphysical properties of droplets in the cloud-based region of liquid water cloud layers have become possible, as it is stated in Jimenez's dissertation. Therefore, this method can significantly contribute to aerosol cloud interaction studies that, according to the latest IPCC report, still remain one of the most uncertain radiative forcing parameters. Now, when the LiDAR beam enters the cloud, it enters a region where multiple scatterings occur due to the presence of the droplets. And this is something that we can see in the first picture as a halo around the LiDAR beam. So from the presence of the droplets makes the light to be backscattered from greater angles instead of from small ones. So the plane of the electric field of those photons that are scattered from greater angles changes, and the polarization of the received light is different, even though the scatterers are spherical. By using a second telescope with a wider field of view, we're able to detect and record these multiple scatterings. So the narrower field of view, the far-range channels, can record mostly scatterings from small angles, therefore light with almost no change in its polarization. But the near-range channels with a wider field of view can capture those photons that backscattered from greater angles, so their polarization changed. So by calculating this dual field of view ratio, delta rad here, which is equal to the depolarization according to the far-range channels with a narrow field of view, divided by the depolarization according to the near-range channels with a wider field of view of the 532 channels, we can estimate the effective radius of the droplets, the light extinction in the cloud, the liquid water content, and the droplet number concentration at a reference height, which is between 0 to 100 meters above the cloud base. Now here I have two cases from Cyprus with two different cases. One, the dominant particles are marine, and the left one, and the right one, the dominant particles are Saharan dust. The first plots here show the range-corrected signal at 532, and we can see for the marine case, a stable cloud layer for almost 13 hours at 2 kilometers, and some sparse clouds at 4 kilometers for the dust case. The next row is a volume to polarization ratio at 532. And the next one is a total concentration number of the cloud condensation nuclei, or else the total number of the aerosols below the clouds. Now here again is a volume to polarization ratio. And here the next graph is the droplet number concentration that I'm going to comment later in the next slide. And below is the extinction, the particle extinction coefficient. For the marine case, mainly non-dust particles are detected, no dust particles. And for the dust case, we see here the extinction coefficient for dust and non-dust particles. And below is the average concentration of the aerosols, again for dust and non-dust, and the colors below can show the aerosol type. And the values of the extinction coefficient in the marine case are mainly between 10 to 100 particles, yes, megameters to minus 1, whereas for the dust case, the extinction coefficient of dust is mostly between, it's close to 10 megameters to minus 1. The average concentration for the marine case is close to 1,000 cloud CCN per cubic centimeter, whereas the dust concentration is around 100 dust particles per cubic centimeter. Now, here are the plots that show the cloud microphysical parameters. The first one is the light extinction coefficient inside the cloud, which is for the marine case mainly between 20 to 30 per kilometer. This is also the case for the Saharan dust, but also some greater values are recorded, close to 40. Next is the liquid water content, that also the liquid water content and the effective radius of the droplets are higher in the case of the marine particles, with values of 0.1 and between 0.1 and 0.2 for the liquid water content and 10 micrometers for the case of the effective radius, in contrast to values mainly below or close to 0.1 grams per cubic meter for the dust case, and an effective radius smaller, that is, it is close to 5 micrometers. The droplet number concentration, however, is lower in the marine case, with values below 100 droplets per cubic centimeter, whereas in the dust case, higher values are recorded with values mainly greater than 100 droplets per cubic centimeter, and even 1,000 droplets are recorded. Now, some of the main conclusions is that the dual-fluid of view depolarization approach can give crucial and detailed information of the aerosol cloud interactions just by using LiDAR products. Marine particles are found to be better cloud condensation nuclei instead of dust, and I say this because even though there were many dust intrusions in Cyprus, very few cases of liquid water clouds were found in dust, but many cirrus clouds were found, so dust acts better as an ice nucleating particle. In general, smaller droplets were found in dust cases, but higher droplet number concentration, so clouds that formed in dust have a greater albedo. And as a next step, the information of the vertical wind needs to be implemented in order to examine how wind updrafts or downdrafts affect cloud formation processes. Thank you.
Thank you very much, Konstantinos. This is a very, very nice talk, and I would have a lot of questions to ask you, but unfortunately, we've passed the time, so I will have to move to the next speaker, who is Vanderlei Martins, who is going to discuss the synergistic measurements from satellite and in situ sampling for air quality applications. It's Vanderlei here.
Franco, we cannot see them on the participants list at the moment. I am aware it's USA time, so maybe they are maybe it's a bit too early. What we should do, maybe we could just move on to the VPICO, and then if they do show up towards the end, perhaps if we have time, we can let them present.
Okay, or maybe I could ask a question to Konstantinos.
Yes, of course, you can ask one question. We have time if they don't try. I mean, if you could ask one question and maybe, yeah, and keep it
Konstantinos,
short.
are you still here? It's not here anymore. Okay, so yes, let's do as you say. So I will. This ends then the session on aerosol and cloud optical properties, unless Vanderlei shows up after the PICOs. So thank you to all the speakers, and now I hand the.
Sorry, you asked a question.
Yes, Konstantinos, are you here?
Yes.
Konstantinos, sorry. Since the next speaker is not here, I wanted to ask you, how do you explain that in the case of dust, you have more droplets, even though you have less aerosol particles, so less condensation nuclei? And also, you said that the particles are smaller. How can you? Do you have an explanation for this?
The droplets are smaller.
Yes. Why?
Yes. Dust is it's a good CCN.
But marine particles are good as well.
Yes, they're good as well. But yes, I think the answer may be that dust is better. But I said that it is not so good because not so frequent we see liquid water clouds in dust. But yes, when we have clouds in dust, then we have greater number concentration of droplets. So more droplets are created.
Okay. Yeah, that's what you said. That's what you said. That's what you observed. Yes, but I was trying to understand the reason, the physical reason. Okay, thank you very much.
Thank you.
Thank you very much. So this ends as I said, the session on aerosol and in situ. No, what was it? Aerosol and cloud optical properties. And I'm now handing over to the PICO session, which is chaired by someone else. So Eleni, maybe you take over.
Thank you, Franco. Many thanks. Thank you to all the speakers and to Franco for chairing the session. Our last session, our VPICO sessions, will be chaired by Dr. Ulrich Bundke. Ulrich, are you here? Excellent. I will be sharing the slides, and then you introduce our speaker. So you can, let me just give me a second to share the slides.
Thanks, Eleni.
Thank you.
So, in the last session, we'll have a firework of 25 minutes, 9 pitches. Eleni, I'm right that 3 have not introduced their slides to you? Okay.
That is correct. We have 3 missing, so unfortunately,
So in
won't be able to go ahead.
principle, we could be a bit relaxed, but nevertheless, it's 2.5 minutes we'll have to go through. But we will expect a firework, as I said, of interesting talks, spanning from the energy transition issues associated with hydrogen, with leaks, how to measure hydrogen. We'll come back to the dust issue, how to measure it on UV dunes, on satellites, and with the new techniques of aerotapes. We'll also have a look on the quantification of trace gas measurements. We'll step over with a model which have a resolution of 25 meters, really challenging things. And we'll end in the Senegal with following the street vendors there and their issues with the traffic. So let's start right over, and we'll start with Doreen Schell on hydrogen leaks detection at PM level in real time at the industry sites. The floor is yours.
Yeah. Hello. My name is Doreen Schell. I'm currently a master's student at Heidelberg University, and I work together with LSE in France. And today I'm going to talk to you quickly about hydrogen measurements at low concentrations at industrial sites. So currently hydrogen is a key alternative energy carrier, but it's also an indirect greenhouse gas. So as the hydrogen production grows, monitoring at low concentrations becomes more important. But traditional mobile hydrogen sensors have mainly safety purpose and measure therefore at percentage levels or generally high levels. But atmospheric monitoring requires much lower detection, such as ppb or at ppm levels. So to bridge this gap, we here present a new mobile hydrogen measurement device, which you can see on the pictures on the left side, which is a mobile gas chromatograph. It has a detection limit of about 1 ppm. And unlike other hydrogen measurement methods, it delivers real-time calibrated data directly on site with a fast response. So we tested this setup at 2 industrial sites in southern Germany, where hydrogen is stored and distributed. And the instrument there successfully identified concentration enhancements across different areas of those facilities. So I have one example here, which are measurements done in the compressor room of one of the sites, or measurements inside and outside of the compressor room. And there we found emissions that the facility's existing safety monitors could not capture because they are designed for higher concentration thresholds. So to sum up, we here have a novel mobile instrument that enables real-time calibrated detection of low concentrations of hydrogen leaks at industrial sites. And measurements are also possible at a distance if the emissions are high enough or if they accumulate. And right now, our next step is to move from the leak identification, which already works well with this mobile instrument, to a precise leak quantification by combining this mobile micro-TC with Flask or ERCO sampling. So, thank you.
Thanks, Serene. Perfect in time, I would say. Great. Unfortunately, during the firework, it's too loud to ask any questions, so we have to move on. And so we come to Kenneth Teshon from the Cyprus Institute, and he will show up new UAV observations to assess the dust particle morphology and orientation. Please, Kenneth, the floor is yours.
Thank you. Can you just confirm that it's possible to hear me?
Yes.
Okay, wonderful. So welcome to this short talk from my side. My name is Ken. I'm a PhD student at the Cyprus Institute and the Technical University of Darmstadt. And we have heard Franco's and Alkistis talk about atmospheric dust. So I would like to build up on this. So just as a quick reminder, we know that dust is non-spherical, which is one of the biggest challenges we have. And we know that it's very abundant in the Earth's climate system. So we want to understand better how this main aerosol works and what are its impacts. So I'm focusing on the fundamentals of dust, which is one, the orientation, and second, the shape. Let me just quickly explain what orientation means. So there are some studies that assume that particles are oriented in a certain way, meaning they can be oriented, for example, horizontally or vertically in the atmospheric column. And I have one instrument called cobalt backscatter sonde, which is mounted on a UV and two different angles. So we have this horizontal instrument shown on the left picture and the vertical instrument. And either instrument has two wavelengths, one on the blue spectrum and one on the near-infrared spectrum. And what we simply do is we fly this drone during strong dust events in the tropospheric, like let's say in the boundary layer and the free troposphere. And what we do is we want to find out if the particle has, if the particles have orientation, and we simply compare the cross section, and we want to see if the cross section differs between these two pointed instruments. And this is how we want to infer the particle orientation. And the second technique is the shape. We are mounting these impactors on another drone, flying again through heavy dust events. And then we are having this very nice additionally device, which is a TEM grid you can see on the second picture. And this grid is mounted on the impactor. And the idea is that particles are impacted on this grid. And I will take a look at the grids under transmission electron microscopy. And this way, we can find the shape within a three-dimensional picture because the ray of the electrons can go through the grid. And that's the main advantage of this. This has been tested during the spring campaign, and I'm happy to let you know about the outcomes in the future.
Great. Thanks, Kenneth. Almost perfect in time. Greetings to Konrad Kantler from my side.
I will.
Thanks a lot. So we'll stay at the dust part, and we'll move on to the aerotape, a novel technology for real-time quantification and characterization of dust and its sources by Eleni Kolinski. Please, the floor is yours.
Hello, can you hear me?
Yes.
Okay, great. So hello, my name is Eleni Kolinski. I'm also a PhD student at the Cyprus Institute, and today I present to you aerotape, a novel technology developed for real-time quantification and characterization of atmospheric dust and its properties. First of all, to begin, it's essential to determine whether coarse particles are suspended by local activity, like traffic suspension, or originate from long-range sources, like desert dust. This distinction is crucial for meeting the air quality standards and for implementing effective mitigation strategies. What sets aerotape apart from conventional optical particle counters is the detection method. While optical particle counters use lasers or detectors to estimate the particle size, the aerotape uses an inbuilt camera microscope to visually capture the particles and analyze their size, shape, and color. The particles are collected on a transparent adhesive tape, and every 10 minutes, the system takes two types of images, as you can see. The first type is LAT images against a black background, optimized to detect light color particles like mineral dust, and trans images against a transparent background, better for detecting darker particles, typically linked to combustion or traffic emissions. These images are analyzed in real time by an AI algorithm that classifies the particles based on the size and the color, which provides a new multidimensional view of the particulate matter composition. To assess precision, we operated two aerotape units side by side during a 3-month winter campaign. The results showed high consistency, indicating a strong repeatability of the instrument. For accuracy, we compared the aerotape's 24-hour averages with the FIDAS reference instrument. The correlation coefficient was 0.78 in the same winter campaign, and this demonstrates that aerotape not only provides reliable internal measurements, but also aligns well with established reference data. Looking ahead, we are expanding field trials to both urban and desert environments, and this will help to further refine the aerotape's classification system and build a robust database of particle sources with the goal of making aerotape a valuable tool for air resource quality. Thank you very much.
Wow, perfect in time. Great. Yeah, we stay with the dust, and we'll go upstairs to the satellites, and so we'll get an insight to this by Zuyer Bona. He's also part of the DustDN project, and we have seen in the last sessions. So the floor is yours.
Okay. Hi, I'm Zohair. I just started my PhD. Do you hear me?
Yes.
Okay. I am Zohair. I just started my PhD last week in Cyprus Institute as part of DustDN. It will be about global dust estimation from novel space missions. Our goal is to estimate the pure dust component in aerosol and the related microphysical parameters. We will be using the data from EarthCare, which is a new satellite launched in May last year as a collaboration between ESA and JAXA. It have 4 scientific instruments, an atmospheric LiDAR providing vertical profiles of aerosol and thin cloud operating at wavelengths of 355 nanometer, and has a high spectral resolution receiver and a depolarization canal. It also have a cloud profiling radar and a broadband radiometer and a multispectral imager. We hope to reduce uncertainties in the estimation of dust component, as was mentioned before by my colleagues, that there is still uncertainties regarding that. Also, to estimate the global trends for dust, we will also use ground LiDAR and other sources if needed. And we also interesting in cloud aerosol interaction, like we will hope to measure parameters like cloud condensation nuclei or ice and ice nucleation particles. Thank you, and we'll keep you updated.
Thanks a lot, Zuyer. We might have time for a question. So, are you planning to, for example, to get also actress stations in a more broad way active to your validation of the satellite?
Yes, we will compare the EarthCare data with old data from Calypso, for example, and from other sources.
Maybe in the future also from Yagos, which I'm responsible for.
Yes.
So thanks a lot.
Thank you.
Yeah, now we are coming to the next pitch. It's from it's a fast fine scale hourly air quality mapping using hybrid dispersion and KNN approaches by Lucas Busch from Atmo Hauts-de-France, which gives us insight to a model downscaling to 225 meters. The floor is yours.
Yeah, thank you very much. Do you hear me?
Yes.
Perfect. So hello everyone. My name is Lucas Boucher, and I'm pleased to present you a method developed by Atmo de France, which is the air quality observatory of the Hauts-de-France region in France. So I'm gonna present you a method. And so the objective of the method was to develop a computational chain that takes into account the temporal and spatial variability of the concentrations of the pollutants from two high polluting human activities, mainly industrial activity and road traffic. And the challenge was to develop this method at a low cost. And also the other challenge was to develop a method that forecast hourly concentrations at a very high spatial resolution, exactly 25 meters. And so the idea was to combine two approaches, a statistical method, which is the k nearest neighbors algorithm, and a physical approach, which is ADMS urban, which is a widely used tool to model air quality. And in this method, we made the assumption that the air quality can be decomposed into three concentration layers: a background concentration layer, an industrial concentration layer, and a traffic concentration layer. And the idea was to estimate the traffic and the industrial concentration layers that are derived from ADMS urban. You can see on the right the results of the method, where we can see the nitrogen dioxide concentrations at different time steps, 8 a.m., 1 p.m., and 6 p.m. And we can see really the variability over time at different time of the day. And below we can see the industrial plumes that are represented in Dunkirk in the north of France. And it is very nice because we take also into account the wind speed. And the method is also very efficient, as we have divided our computational time by 100. So if you're interested in the article, you can see on the corner on the left of the slide, there is the link to the article. Thank you very much.
Thanks for this. Impressive, reducing computational times by a factor of 100. Wow. Okay, but we have to move on. So now we come to the group of Andy Ruth and the dual cavity, dual comp interferometry with incoherent light given by Johnny Brow.
Yep.
The floor is yours.
Yep. Can everybody hear me?
Yes.
Yeah. Okay. Good. Yeah, my camera isn't working, unfortunately. But yeah, here we go. Hello, everybody. I'm Johnny Brow, a fourth-year PhD student in the laser spectroscopy group at University College Cork. And I'm here to present the work on dual cavity, dual comb interferometry, a method that we have successfully developed recently. High-resolution broadband absorption spectroscopy, like Fourier transform spectroscopy, is often the method of choice for atmospheric trace gas detection due to its good selectivity, versatility, and the fact that multiple gases or isotopologues can be detected at once. On one hand, dual comb spectroscopy is a powerful approach for this that has attracted a lot of attention in recent years, but it requires frequency combs that are generally expensive, and maximizing its sensitivity through the use of optical cavities poses significant challenges. On the other hand, incoherent broadband cavity-enhanced absorption spectroscopy is highly sensitive and experimentally straightforward. It just requires an incoherent light source, an optical cavity, and a wavelength selective detector. The resolution, however, is limited by that detector, which also tends to become very expensive and bulky when very high resolution is desired. Dual cavity, dual comb interferometry combines the two methods. We couple light from a high power, broadband, incoherent light source into a pair of optical cavities with slightly different lengths. This simultaneously generates a pair of frequency comb-like structures and at the same time improves the sensitivity through the usage of two optical cavities. This creates an experimentally simple, high resolution, high sensitivity spectroscopic technique. As a proof of concept, we have detected acetylene, CO2, and water vapor in the lab with an integration time of 200 milliseconds at a resolution of about 300 megahertz. A UK patent application has been filed, and I'd like to thank you all for listening.
Thanks, Jerry. You expect that this will be coming to the to Caribbean, Yagos Caribbean part in the future sometimes?
It is possible. It is not currently on a radar since it's still very much it's an early prototype. Right? But it's definitely a possibility, but I'm not going to confirm anything.
Keep fingers crossed.
Exactly.
Thanks a lot.
Thank you very much.
Perfect in time. Now we come to the ammonia sensors for UAV and UAV, a comprehensive assessment of ground-based and aerial ammonia measurements at the poultry farm in Northern England. Claire Pearson, it's your floor.
Hi, can you hear me okay?
Yes.
Brilliant, thank you. Afternoon, everyone. My name is Claire Pearson from UKCEH, and I'm pleased to be talking to you today about an exploratory field campaign we did using miniaturized low-cost ammonia sensors on drones or UAVs. As most of us probably know, ammonia is a key air pollutant driving ecosystem degradation and particulate matter formation, but it's chronically challenging to monitor reliably in the field, partially because it varies a lot over space and time. So we wanted to see what we could do if we put a sensor on a drone. So to do that, we collaborated with a drone engineering company called Limacero to test the feasibility of measuring ammonia using sensors integrated onto the drones. In our experiment, we deployed a TB600 ammonia sensor in 3 different configurations, but I'll just be focusing on the drone mounted setup today. Our study site, you can see on the map there, was between 2 poultry sheds in Northern England, and these were emptied during our field campaign, which is usually a really high ammonia emission event, so reasonably good conditions. We had a static meteorological station, which was about 8 meters above ground, and a fixed wing drone, which had the TB600 on it. We managed to get in 14 flights over 2 weeks in December of 2024, and these range from 21 to 49 minutes. These are relatively short answers because the time of year being in Northern England meant we couldn't get our solar drone, which had longer flight times, up in the air. There just wasn't enough sunlight. We then analysed the flight data, looking into concentrations in different weather conditions, elevation, and mapping ammonia heat maps, and trying to identify where the emission sources were coming from using non-parametric wind regression, which you can see on the slide there. So during this experiment, we identified a few challenges. The TB600s do have some limitations in this particular use case. The relatively high limit of detection meant that sort of background or ambient ammonia concentrations weren't very well captured. And we also found the concentration data was relatively sort of qualitative, so it's hard to give absolute values. There was a little bit of a lag in the sensor response time after exposure, which meant with a sort of drone that was moving very quickly, the actual location of where each concentration point was measured was a little bit uncertain. And longer flight times would have been better if we did it in a better time of year and improve our confidence in the measurements. Despite this, we were able to detect clear spikes when going over the emission sources, and we were able to map potential emission hotspots and identify plume directions. Overall, the study showed that drone-mounted ammonia sensors can offer high spatial coverage, especially in places where monitoring is sparse, but the technical constraints should be addressed before we can actually use this for modelling or regulatory purposes. But overall, it's a promising proof of concept and points towards a need for sort of more robust, responsive, and well-calibrated sensor systems that can exist on drones going forward. Thank you.
Thanks a lot, Claire. And sticky components, yes.
Yeah.
So now we have to skip 2 of the next slides, and we're coming to the last one. Traffic-induced atmospheric pollution and associated health impacts, a pilot study from the streets, fruits, vendors by Bertrand Taché from Diop University. The floor is yours. We can't hear you. Yeah, now.
Are you hearing me now?
Yes.
Okay, good. Thank you very much. Yes. Hi, everybody. So my name is Bertrand Chong. So I'm going to introduce you my work here in Senegal. So at the moment, we're working on traffic pollution, and we have been looking at the impact of the people who are selling goods close to the streets. So we work in the city of Thiès here in Senegal. The first thing we did is that we went to the street and we saw that a lot of people, women and men, are selling a lot of fruits, okay, just near to the roads, and they are very exposed to the air pollution. So we went there, we talked to them, and we invited them to be part of the study. So we gave them a kind of interview, okay, I would say, with few questions, and then afterward we went to install an instrument close to them in order to assess the pollution. And so what we discovered is that most of them, they are really exposed. And we found out that the level of PM 2.5, for instance, is very high, maybe 4 or 5 times the level allowed by the World Health Organization. And we found also that more than 40% of people who are selling those fruits have symptoms related to respiratory diseases. They have a headache, they have cold, cough, and so on. So they are really let's say, facing serious health issues there. So our conclusion is just that the government should do something with these people. They have to make, let's say, adopt a kind of policy in order to protect those people and inform them about the risk of selling goods, let's say, close to the roads. So this is where I end. Thank you very much.
Thanks a lot, Bertrand. So this brings us to the end of this pitches. I'm very, very glad that everybody stayed in the time. We have, I think, if the non-show up presenter from the last session is here, that he can present. Eleni, is he there now? Otherwise, I give you the floor and say goodbye from Jülich.
Thank you, Ulrich. I cannot see them. Maybe they haven't been able to connect in the end, unfortunately. Vanderlei, are you here? Let's give them the last shout, and then if not. Okay, I don't think they're here. Thank you, Ulrich. Thank you. Well, thank you everyone for joining us. Thank you to all the speakers, the chairs, all the attendees, the organizers, and see you at the next one.